In this lesson, we want to review the addition property of equality. So for the majority of you taking the course, you fully understand how to solve a linear equation in one variable. But again, it might have been some time since you've kind of gone through the steps, and you might not have fully ever understood it. So it's just good to get a review in before we look at anything that is more challenging. So a linear equation one variable is just defined as something like ax plus b equals c, where a is said to not be equal to 0. So you have this guy right here, this a, which is the coefficient of x. You have b and c, which are constants. And all of those can be any real number that you want. So a, b, and c can be anything you want with the exception of a, which cannot be 0. The reason a can't be 0 is because it's multiplying the variable. And if 0 was multiplying x, well, then you'd have no variable involved. So that would be an issue for us. Now, a linear equation of one variable is sometimes called a first degree equation because the largest exponent on the variable is a 1, right? And some of you remember that quadratic equations, where the largest exponent on a variable is a 2, are sometimes called a second degree equation. Okay, so it's the same concept there. So a few examples of a linear equation one variable, something like 2x minus 5 equals 11, where a here would be 2, b would be negative 5, and c would be 11. Or something simple just like x equals 19, right? Here a would be 1, b would be 0, and c would be 19, right? So something like that. Or you could have some fractions involved. You could have something like 1/4 x plus 1/9 equals 23/17. Okay. Here a would be 1/4, b would be 1/9, and c would be 23/17. So when we work with equations, we need to understand the basic definition. So we're saying that two algebraic expressions are set equal in value. So this algebraic expression here of 2x minus 3 is set equal to this algebraic expression here of 7. So this guy and this guy are each algebraic expressions. But the whole thing, because of the equality, is known as an equation, right? So the 2x minus 3 is equal to 7. Now, when we solve an equation, and we'll talk about this more in a moment, we are basically finding the value or the values that when we replace the variable or the variables gives us a true statement. When we say gives us a true statement, it means that the left side of the equation has the same value as the right side of the equation. So they are the same. So in this example here, I've given you the solution. So x is equal to 5. That means that I can plug a 5 in here for x, and that will give me the same value on the left as I have on the right. So let's try that out. So we have 2 multiplied by, plug in a 5 for x, then minus 3 equals 7. I would just simplify each side. 7 on the right, I can't do anything with that. On the left, 2 times 5 is 10. So you'd have 10 and then minus 3. 10 minus 3 is 7. Let me kind of write that a little better. Again, 10 minus 3 is 7, so we would say 7 is equal to 7. And that's true. 7 is the same or is equal to 7. So this is a true statement. Now, if you plug something in for the variable and it's not the correct solution, you will not get a true statement. So let's say that I said that x was 4 as an example. So let's erase this and this and this. We'll put a 4 here. 2 times 4 is 8. 8 minus 3 is 5. 5 does not equal 7. So this would be false. Okay, this would be false. So when you work with a linear equation in one variable, you can always check to make sure you got the right answer. You just plug your proposed solution in for your variable, and then you make sure you have the same value on the left as you have on the right. So let me put this back to the way that it was so that it's correct again. So again, we said this was a 5. And so this would be 10, and this would be 7, and this would be true. So in most cases, we are not going to be just simply given our solution. We have to go through a series of steps to obtain our solution. Again, when we solve an equation, we are finding the value or the values that make the equation true. Your ultimate goal when you're solving an equation is to get the variable you're looking for, in this case it's x, equal to some number. That's when it's solved. Okay, x equals some number. That is the value I can plug back in for x, again, that makes the equation true. So if you want to write something down, you would say that your goal is to isolate the variable. Okay, so isolate the variable on one side of the equation. So there's a few properties we can talk about real quick that'll get us all the way there. So the first thing is that adding a number and its opposite will always give you 0. The second thing is that adding 0 to a number leaves it unchanged. And the third thing is that we can add or subtract the same value to or from both sides of an equation and not change the solution. So that last property is known as the addition property of equality, and that's the focus of our lesson today. So if I have something like, again, x minus 7 equals 13, and I want to isolate the variable, I want to undo what's being done to x. If it's subtraction, I want to think about addition. If it's addition, I want to think about subtraction. If it was multiplication, like we'll see in the next lesson, I want to think about division. If it was division, I want to think about multiplication. Here I'm subtracting away 7, so to undo that, I just want to add 7. Because negative 7 plus 7 gives me 0. Again, the additive inverse property. And then if I had x plus 0 on this side, that's just equal to x, right? 0 is the additive identity. So let's go through this guy. Again, I'm subtracting away 7. So I would start by adding 7 to kind of counteract that. If I'm subtracting away 7, I add 7. But then to make it legal, I've got to add 7 on the right side as well. So I did this to this side and this to this side. You think about that as maintaining the balance. If I add 7 to the left, I've got to add 7 to the right, and then I'm good to go. So now it's pretty simple. If I have minus 7 plus 7, or you can think about that as negative 7 plus 7, that's just 0. So I have x plus 0 is equal to 20, which is just x equals 20, right? So that's our solution there, nice and easy. And you might see people, or you might see your textbook, write your solution like this. This is known as solution set notation. It's not something we're going to use too much throughout the course, but I just want you to know that it does exist in case you see it. You're not wondering why, it's notated differently or wondering if you made a mistake. It's just different notation. So we can always check this, again, by plugging in a 20 for x and making sure we have the same value on the left as on the right. So I would have a 20 minus a 7 equals 13. 20 minus 7 is 13, so 13 equals 13. So yes, this is true. This is true. We have the right answer. And again, for this one, it's so easy, you could just eyeball it. What number minus 7 gives us 13? Well, 20 does, right? 20 minus 7 is 13. So we know we have the correct answer here. All right, let's take a look at another one. So we have x plus 11 equals negative 34. Again, our goal is to isolate the variable. Okay, so how do I do that? I have plus 11 here. If I'm adding 11 to x, how can I undo that? Just subtract 11 away, right? If I have 11 minus 11 or 11 plus negative 11, I get 0, right? So it's gone, right? I'd have x plus 0, which is just x. So I'd have x plus 11 and then plus negative 11. Or if you want to, you could just put minus 11. It doesn't matter. It's the same thing. And then is equal to, you have negative 34. Because I did it over here, I've got to do it over here. Okay, you've got to maintain that balance. Again, that's the addition property of equality. You can add the same number to both sides of the equation. So over here, I can just cross this out and put a 0, right? It's just basically canceled. You're left with x, and this is equal to negative 34 plus negative 11 is going to be negative 45. Again, we can check this. We think about plugging in a negative 45 for x there. So if I had negative 45 plus 11, does that equal negative 34? Yes, it does. Negative 45 plus 11 is negative 34. So you get negative 34 equals negative 34. So this is true. Right? We can just check that off and say true. All right, let's look at one that's a little bit more challenging. So we have 2x minus 7 equals x minus 3. So you can still just solve this with addition or subtraction. And again, our goal is to isolate the variable. Always think about that. We're isolating the variable. So how do I isolate the variable here? We have 2x minus 7 equals x minus 3. Well, the first thing is I've got to get all the variable terms to one side, and then I want all the numbers on the other, right? That's going to give me the possibility of having x equals some number. Right now I have an x involved in this guy here and an x involved here. So I've got to move this over here. And the way I can do that is I can use the addition property of equality. I can add negative x to both sides of the equation. So I can say this is 2x minus 7 is equal to x minus 3. Again, all I did was I subtracted x away from each side. Or again, you could write this as plus negative x Doesn't matter, whatever is more convenient for you. X plus negative x is 0, so this is gone. I now have 2x minus 7 is equal to negative 3. Now I can simplify because 2x minus x is just x. So I have x minus 7 is equal to negative 3. And now all I need to do is think about the fact that negative 7 is being added to x, or you can think about that as 7 being subtracted away from x. So I want to add 7 to each side of the equation. So I'm going to do this in vertical format because it's a little bit simpler. So I'm going to put plus 7 here and then plus 7 here. It's just a more compact way to do it. This is going to cancel, and I'm going to end up with x is equal to, over here, negative 3 plus 7 is going to be positive 4. So if we wanted to check this, let me erase everything. So I would plug in a 4 for this x here and this x here. So it's got to be for each occurrence of the variable, okay? So I would have 2 multiplied by 4 minus 7 is equal to 4 minus 3. 2 times 4 is 8. So you'd have 8 minus 7 over here. 4 minus 3 is 1. 8 minus 7 is 1. So you get 1 equals 1. This is true. Okay? So we know our solution here, x equals 4, is correct. In this lesson, we want to review the multiplication property of equality. So in our last lesson, we reviewed the addition property of equality. Now this property allows us to add or subtract the same value to or from both sides of an equation. So generically, if we have something like, let's just say A equals B, we could say with the addition property of equality, I can add C to each side of the equation and maintain that equality, right? It's still true. So this allowed us to solve basic equations with just addition and subtraction, right? One-step equations, very, very simple. Something like x minus 11 is equal to, let's say, 17. What I want to do when I solve an equation is just isolate the variable on one side. So if I want to isolate x here on the left side, I've got to undo what's being done to it. Here I'm subtracting away 11, so the opposite of subtracting away 11 is adding 11. So I'm going to use my addition property of equality to just add 11 to each side of the equation. So I would have x minus 11 plus 11 equals 17 plus 11. So again, notice how I did it to the left and also the right. That's what made it legal. Over here, negative 11 plus 11 is 0. So I can just say this is x over here. So I've isolated the variable. And then here, 17 plus 11 is going to give me 28. So x here would just be 28, right? 28 minus 11 does give me 17. So this is in fact the correct solution. Now we're going to see more complicated linear equations, obviously, and we need more tools than just the addition property of equality. So in this lesson, we're going to review something known as the multiplication property of equality. And this property basically tells us that we can multiply or divide both sides of an equation by the same non-zero number and not change the solution, okay? So the reason I say non-zero number is if you multiply both sides by 0, you get 0 on each side, right? It's done for. If you divide by 0, it's undefined. So you have to put 0 in as a restriction there, okay? So you got to maintain that. So essentially what we're saying here is that if A is equal to B, then A multiplied by C is equal to B multiplied by C. So you maintain the equality, even though you've multiplied both sides by that same value C. We would specify here that C does not equal 0, okay? So how can I use that to solve something like 3x equals 12? Well, let's erase this real quick. And again, I want to write down my goal here, which is always, always, always to isolate the variable. Okay, we want to isolate the variable. Very important to remember that. Stay focused on that goal. Well, if I want to isolate the variable x, what's being done to x right now? X is being multiplied by 3. So how do I undo what's being done to the variable? Well, if I'm multiplying by 3, I just need to divide by 3. And again, the multiplication property of equality lets me divide both sides of the equation by 3. So that's legal to do as long as I do it by both sides. So 3x divided by 3 is equal to 12 divided by 3. Now, 3 over 3 is 1, right? Any non-zero number divided by itself is 1. We already know that. Multiplying by 1 leaves a number unchanged. So essentially this becomes 1 times x, or just x, right? 1 is the multiplicative identity. So I can just write x here. I don't need 1x. This is equal to 12 divided by 3, which is just 4. So I get x equals 4 as my solution, right? So I can plug a 4 back in for x here and verify that I got a true statement. So 3 times 4 is equal to 12. We know that is correct, right? 12 equals 12. So we can go ahead and say that this guy is true. Okay? Check that off and say, yes, x equals 4 is the correct solution. All right, let's take a look at another one. So we have x divided by 5, or you can say x over 5. It's in fractional form. This is equal to negative 20. So again, what's being done to x? We want to undo that so that we can isolate the variable. If you just write this down each time, it's very, very simple to go through the steps and figure it out. If I want x by itself and it's being divided by 5, just undo it, right? What can I do to undo division? Multiplication. So I would multiply both sides of the equation by 5. So x over 5 times 5 is equal to negative 20 times 5. And so this 5 would cancel with this 5. 5 over 5 is just 1. 1 times x is just x. And this equals negative 20 times 5 is negative 100. Okay, so we're good to go there. Now, you can check this. Plug in a negative 100 for x. So negative 100, divide that by 5. This should be equal to negative 20. And it is, right? You get negative 20 equals negative 20. So yes, this is a true statement. So we can check that and say, yes, this is true. All right, let's take a look at another one. So for this one, we're going to do some simplifying first. We have 3x plus 6 plus 4x equals negative 15. So in any equation, you can always simplify things before you get going. And in this case, I know 3x plus 4x is 7x. So this is 7x, then plus 6, which is equal to negative 15. Now, I can't solve this in one simple step, but I can solve it in two. I'm going to use both of my properties here. I'm going to use my addition property of equality, and I'm going to use my multiplication property of equality. Now, a lot of you would say, okay, 7 is multiplying x. Let's go ahead and undo that. Well, you can solve it that way, but it's going to be much more complicated. The first thing you want to do is get rid of this plus 6 part here, okay? You always want to isolate the variable term first, and then you can isolate the variable itself. So if I want to get rid of this 6 here, since it's being added to 7x, I just subtract it away. So 7x plus 6 minus 6 is equal to negative 15 minus 6. So over here, if I look at this, 6 minus 6 is 0. So I have 7x is equal to negative 15 minus 6 is going to be negative 21. So now I recognize this format from the last two problems. I have a single operation that I can do to get x isolated. 7 is multiplied by x, that's why you say 7x, and this is equal to negative 21. Well, if I'm multiplying x by 7, all I need to do is divide by 7 to undo that. So this would cancel with this. 7 over 7 is 1. 1 times x is just x. And then negative 21 divided by 7 is negative 3. Okay, so x equals negative 3 here. So we can plug in and check. So let me erase all this. Since we have more than one instance of x here, we've got to make sure we plug a negative 3 into each copy. Okay, so we have 3 times, plug in a negative 3 for x, and then plus 6 plus 4 times, plug in a negative 3 for x, and then we have is equal to negative 15. 3 times negative 3 is negative 9, plus 6 plus 4 times negative 3 is negative 12. So you can put plus negative 12, or you can just put minus 12. This should equal negative 15. Negative 9 plus 6 is negative 3. Negative 3 minus 12 is negative 15. So you get negative 15 equals negative 15, which is true, right? This is true. So you can go ahead and check this guy off and say x equals negative 3 is the correct solution. All right, let's take a look at one more of these. So we have negative 22 plus 56x minus 35 is equal to negative 169. So again, I can simplify on the left here. Negative 22 minus 35 is negative 57. So I would have 56x minus 57 is equal to negative 169. So before I do anything here, I want to realize that I want to isolate the variable term before I isolate the variable itself. It just makes things easier. So what I'm going to do, since I'm subtracting away 57 from the 56x, I'm just going to add 57 to both sides of the equation. Okay, that's all I'm going to do. That's because subtracting away 57 and adding 57, those operations would cancel and become 0. So on the left, I would have 56x, right? That's going to cancel and be 0. And this is equal to negative 169 plus 57 is negative 112. So now I can isolate x by just dividing both sides by 56, right? Since 56x means 56 is multiplying x, to undo that operation, I just divide by 56. So divide the left side and also the right side. So x would be equal to, you have negative 112 divided by 56, which is negative 2. Okay, so that's our solution. And again, we can check this by plugging in a negative 2 for x there. Let me erase all this, and let's drag this up here. And one note I want to give you, if you simplified the problem, that's fine. But you always want to check it in terms of the original problem in case you made a mistake when you were simplifying. That'll help you catch the mistake, right? If you plug it back into something that you incorrectly simplified, you might verify something that wasn't correct, okay? So we want to plug this in right here in the original equation. So we get negative 22 plus 56 times negative 2. Just plug in a negative 2 for x. Then minus 35 equals negative 169. And so 56 times negative 2 would be done first. That's going to give me negative 112. So you would have negative 22 minus 112 minus 35 equals negative 169. Negative 22 minus 112 is negative 134. And then negative 134 minus 35 is going to be negative 169. So you get negative 169 is equal to negative 169. So this is true, right? This is true. And we can say that this guy is the correct solution, right? X equals negative 2. In this lesson, we want to review solving linear equations in one variable. So over the course of the last two lessons, we reviewed the addition property of equality along with the multiplication property of equality. And we looked at how to solve some kind of single-step equations. And towards the end of the last lesson, we looked at some things that were a little bit more complex. But in this lesson, we want to put everything together and show a four-step method that will enable us to solve any linear equation in one variable. So any equation of the form ax plus b equals c, where again, a does not equal 0. So the method starts with step 1. We want to simplify each side separately. So this is just where we combine any like terms, we clear any parentheses we might have. Basically, we get things as simple as we can. The second step is to move all variable terms to one side and then move all constants to the other, okay? So the way you're going to do this is you're going to use your addition property of equality. Then the third step is to isolate the variable. You're going to do that using the multiplication property of equality. And the last step is to check the result. There's absolutely no excuse, if you have time, to get a wrong answer when you're solving one of these equations. It is so easy to check the result. You can make sure right then when you're taking your test that you got the correct answer before you turn it in. Okay, so it's very important to check. All right, for the first example, we have 3x plus 12 is equal to negative 8 times the quantity negative 4x minus 6 plus 4 multiplied by the quantity negative 7x minus 4. So the first thing I want to do again is simplify each side separately. On the left, 3x plus 12, I can't do anything with that. That's as simple as I can make it. On the right, I can clear my parentheses. Negative 8 times negative 4x is going to be 32x. Negative 8 times negative 6 is going to be plus 48. Then 4 times negative 7x would be minus 28x. And then 4 times negative 4 is minus 16. So let's scroll down and get some room going. Now what I want to do is combine like terms over here, because I can still simplify. So on the left, I still have 3x plus 12. On the right, 32x minus 28x is going to give me 4x. Then 48 minus 16 is going to give me 32. So now each side is as simple as I can make it. So my second step is to move all variable terms to one side and all constants to the other. So a variable term is a term with a variable. So 4x is a variable term, and so is 3x. And then constants are just numbers. So we would say 12 is a constant, and so is 32. So I want to move 12 to the right side by just subtracting 12 away from each side of the equation. And so let's just go ahead and say we have 3x plus 12 minus 12 would be 0, but let's just go ahead and show it. So plus 12 minus 12 equals 4x plus 32 minus 12. So again, this guy would cancel and just be 0. So the left side now is just 3x. And this is equal to 4x plus, we have 32 minus 12, which is 20. So I want to move this guy over here now to the left. So I would just subtract 4x away from each side of the equation. So let's just go ahead and say minus 4x and minus 4x. Let's just go ahead and do this vertically because it's a little bit easier. This is going to cancel, right? 4x minus 4x is just 0. On the left side, 3x minus 4x is negative x. Or if you're more comfortable, you can write this as negative 1x. That's fine too. And this is equal to 20. Now my third step, now that I have a variable term equal to a number, is just to isolate the variable. So what's being done to the variable? In this case, you have a negative x, or again, a negative 1 times x. So you can multiply both sides of the equation by negative 1, or divide both sides of the equation by negative 1. In this case, it really doesn't matter. Let's just go ahead and divide by negative 1 on each side of the equation. And so negative 1 over negative 1 is 1. So you have x is equal to 20 over negative 1 is negative 20. So this is our solution. X equals negative 20. So let me erase everything and we're going to check. So again, we said our solution was x equals negative 20. And I'm just going to plug in a negative 20 everywhere I see an x. Okay, we're going to evaluate each side and make sure that we get the same value. So on the left, you'd have 3 times negative 20 plus 12 is equal to, then on the right, you'd have negative 8 times the quantity. You'd have negative 4 multiplied by negative 20, then minus 6, so that quantity there. So then plus, you'd have 4 times the quantity. You have negative 7 times, again, negative 20, and then minus 4, okay, so that quantity there. And let's just go through and simplify. So 3 times negative 20 is negative 60, and then negative 60 plus 12 is negative 48. So let's write negative 48 over here. On this side, negative 4 times negative 20 is 80. 80 minus 6 is 74. So you would have negative 8 multiplied by 74. Then plus over here, you'd have negative 7 times negative 20, which is 140. And then 140 minus 4 is 136. So plus 4 times 136. So this is negative 48 is equal to negative 8 times 74 is negative 592. Then plus 4 times 136 is 544. So if you sum negative 592 and 544, you're going to get negative 48. So you would get negative 48 is equal to negative 48. So the left and the right side are the same value. So we can go ahead and say this solution is correct. X equals negative 20. All right, let's go ahead and take a look at another one. So we have 11 times the quantity 2x plus 3 is equal to negative 3x plus 9 times the quantity 1 plus 3x. All right, so again, we want to simplify each side separately to start. So on the left, I'm going to multiply 11 by 2x, that's 22x. Then plus 11 times 3 is 33. This equals, you have negative 3x. Then plus 9 times 1 is 9. Then plus 9 times 3x is 27x. So on the left, I can't really do anything else. I just have 22x plus 33. On the right, I can combine like terms. I have a negative 3x and a 27x. That would be 24x, and then plus 9. So now that I've simplified each side as much as I can, I want to move all the variable terms to one side and move the constants to the other. What I'm going to do is I'm going to move this guy over here, and I'm going to move this guy over here, okay? So the way I'm going to do that is I'm going to subtract 24x away from each side of the equation. So this guy right here is going to cancel. 24x minus 24x is 0, so that's gone. Then over here, I'm going to subtract 33 away from each side of the equation. And again, 33 minus 33 is 0, so that's gone. So on the left, I have 22x minus 24x, which is negative 2x. Let me kind of straighten that out just a little bit. And this equals 9 minus 33 is negative 24. Negative 24. So now I have a variable term equals some number, okay? So essentially at this point, I just want to isolate the variable itself. So I want to isolate x. And to do that, since negative 2 is multiplying x, I'm going to divide both sides of the equation by negative 2. So let me scroll down just a bit. And so what's going to happen is this would cancel with this. Negative 2 over negative 2 is 1. So you'd have 1 times x, which is just x. And this is equal to negative 24 over negative 2 is positive 12. So our solution here is x equals 12. Again, let's check this. So I'm going to erase everything. So again, we said x is equal to 12. So I'm going to plug in a 12 here, and also here. So we'll have 11 times, inside of parentheses, we have this quantity 2 times 12. plus 3. Okay, so that quantity. And then this should be equal to, you have negative 3 times, you have 12, plus 9 times this quantity. So inside the parentheses, we have 1 plus 3 multiplied by 12. Okay, so that's the quantity there. And let's go ahead and simplify on the left side first to start. So 2 times 12 is 24. 24 plus 3 is 27. So you would have 11 times 27. So this is equal to, over here, negative 3 times 12 is negative 36. And then plus 3 times 12 is 36. 36 plus 1 is 37. So you would have 9 times 37. All right, so let's see what we got here. So 11 times 27 is 297. This should be equal to 9 times 37 is 333 plus negative 36. So negative 36 plus 333 is 297. So you get 297 is equal to 297. So that tells us that our solution here, x equals 12, is correct. All right, so pretty straightforward. Let's just go ahead and look at one more of these guys, and then we'll move on kind of to the next concept. So we have 8 multiplied by the quantity 7x minus 9 is equal to negative 4 times the quantity negative 3x plus 10, and then plus 12x. So again, I want to simplify each side separately. So 8 times 7x is 56x, and then minus 8 times 9 is 72. This equals negative 4 times negative 3x is 12x, and then negative 4 times 10 would be minus 40, and then we have plus 12x. So on the left side, I can't simplify any further. I'm just going to copy what I have. So 56x minus 72. On the right side, 12x plus 12x is 24x, and then minus 40. So now each side is as simple as I can make it. Now I want to move all the variable terms to one side, all the numbers to the other. So this guy I'm going to move over here, and this guy I'm going to move over here, okay? All I'm going to do it in just one step. So I'm going to say minus 24x on each side of the equation. So this is gone. And I'm going to add 72 to each side of the equation. So this is gone, okay? So on the left side, I have 56x minus 24x, which is 32x. On the right side, I have negative 40 plus 72, which is 32. So now I have a variable term, 32x, equals some number, 32. So it's easy to find my solution now. I just want to isolate the variable x. And if 32 is multiplying x, I just want to divide both sides of the equation by 32. So I can undo that. So this is going to cancel with this, and I'm left with x is equal to 32 over 32 is just 1. So x equals 1 is my solution here. So let's erase everything and check. So again, x equals 1 is our solution. So I'm going to plug a 1 in here and here and here. So I would have 8 times, let's just do this on the fly because 1 is easy to work with. 7 times 1 is 7. 7 minus 9 is negative 2. So you'd have 8 multiplied by negative 2. And let's just go ahead and write that as negative 16. We can kind of move on. So over here, if I plug in a 1 inside the parentheses, negative 3 times 1 is negative 3. Negative 3 plus 10 is 7. So you'd have negative 4 times 7, and that's negative 28. Then you'd have plus 12 times 1 is 12. So what is negative 28 plus 12? That is negative 16. So again, we have a true statement because we have the same value on each side of the equation. And so x equals 1 is the correct solution. In this lesson, we want to review solving equations with decimals or fractions. So in the last lesson, we reviewed a 4-step method to solve any linear equation in one variable. In this lesson, we're going to talk about how to clear an equation of fractions or decimals just to make it cleaner and easier to work with. This process of clearing an equation of either fractions or decimals is completely optional. You can work with fractions in an equation. You can work with decimals in an equation. You get the same answer either way. So this is just something that if you want to do it, you can. If you don't have to. So let's start out with an example with some fractions involved. We have negative 2/3 x plus 3/2. And this is equal to negative 5/2 x minus 13/6. So the basic idea here, if you want to clear an equation of fractions, you want to multiply both sides of the equation by the LCD, the least common denominator, of all the denominators involved. Remember, this is legal because I can always multiply both sides of the equation by the same non-zero number. Now, if I look at my denominators here, I have a 3, a 2, a 2, and a 6. So what would the LCD be? The LCD here would be 6. So all I need to do is multiply both sides of the equation by 6. So let's go ahead and set that up. So outside of some parentheses, I put my 6, and inside I'll put my negative 2/3 x plus 3/2. And this is equal to, 6 is going to multiply by the right side as well. So I'll set up my parentheses. So negative 5/2 x minus 13/6. And I'll put the 6 outside here. So I'm just going to use my distributive property here and multiply 6 by each term inside of the parentheses on each side of the equation. So to start out, 6 is going to get multiplied by negative 2/3 x. So 6 times negative 2/3 x. We know that the 6 would cancel with the 3 and give me a 2. 2 times negative 2 is negative 4. So I can go ahead and erase this and put negative 4x here. So next we would see that 6 is going to multiply by 3/2. So I'm going to put plus 6 times 3/2. And what we'll have here is that the 6 will cancel with the 2 and give me a 3. 3 times 3 is 9. So I'm going to go ahead and write this as plus 9 here. So this is equal to, I'm basically doing the same thing over here, multiplying the 6 by each term. So 6 times negative 5/2 x. And we can see that the 6 would cancel with the 2 and give me a 3. 3 times negative 5 is negative 15. So you'd have negative 15x there. So negative 15x. And then lastly, you have 6 that's multiplied by negative 13/6. So I'll go ahead and put minus. You have 13/6 times 6. And I'll cancel this 6 with this 6. And I'm just left with 13 there. So now I have an equation that is fraction-free. And I can go through my normal procedure. Again, if this is something that you don't want to do, you don't have to. Realize that I have to spend the time to clear the fractions. And I could just work with them if I want to. So at this point, I just want to move all the variable terms to one side, all the numbers or constants to the other. So I'm going to go ahead and add 15x to both sides of the equation. So what's going to happen is this is going to cancel. Then additionally, I'm going to subtract 9 away from each side of the equation. And this is going to cancel. Let me scroll down and get some room going. Negative 4x plus 15x is 11x. So that's the left side of the equation. On the right side, negative 13 minus 9 is negative 22. So what I'm going to do is now finish this up by isolating my variable x. Since 11 is multiplying x, I'm just going to divide both sides of the equation by 11. And that's going to give me a final answer of x equals negative 2. Now, you can check this if you want. I firmly advise that you check everything if you have time. In the interest of time for this video, I'm not going to check all of them. I'm going to check just this first one. Okay, so all the additional problems we're going to look at today, I'll leave it up to you to check. So to check, we want to plug a negative 2 in for each occurrence of x in the original equation. So let me erase everything. We're going to go back up. All right, so what we want to do, remember our answer is x equals negative 2. We want to plug negative 2 in for each occurrence of x. So there and also there. So I would have negative 2/3 multiplied by negative 2, then plus 3/2. This is equal to negative 5/2 multiplied by, again, negative 2, and then minus 13/6. Okay, so up here we have negative 2 times negative 2, that's 4. So I would have 4/3 plus, over here, 3/2. And this is equal to, over here, negative 5 times negative 2 is 10. So 10/2. And then minus 13/6. Okay, scroll down, get a little room going. So the idea here is to simplify each side and make sure you have the same value on each side, okay? So I need to get a common denominator going. So between 3 and 2, my LCD would be 6, right? So 4/3 times 2/2 plus 3/2 times 3/3. I would basically have 8 plus 9 over the common denominator of 6. 8 plus 9 is 17. So let's go ahead and write this side on the left as 17/6. And on the right, I would get a common denominator by just multiplying this by 3/3. 10 times 3 is 30. So you would have 30 minus 13 over the common denominator of 6. 30 minus 13 is 17. So you would also have 17/6 on this side as well. So same value on the left as we have on the right. That tells us that our solution x equals negative 2 is correct. Okay, so we can check that one off. So for the next problem, we're going to look at something that's a little bit more tedious. We have some parentheses involved. We have 1/3 multiplied by the quantity negative 3/2 x plus 1. This is equal to 95/12 plus 5/3 x. So the idea here is that if you're trying to clear an equation of fractions and you have parentheses involved, go ahead and clear the parentheses using your distributive property first, and then clear the fractions. So 1/3 times negative 3 halves x would give me negative 3/6x. Then plus 1/3 times 1 is 1/3. This equals 95/12, and then plus 5/3 x. Now, between my denominators here, I have a 6, I have a 3, I have a 12, and I have a 3. So the LCD is just going to be 12. My LCD is 12. So all I got to do is multiply both sides of this guy by 12, and I will clear all the fractions. So 12 times negative 3/6x would be what? I know that 12 would cancel with 6 and give me 2. 2 times negative 3 is negative 6. So this would be negative 6x. Then plus 12 times 1/3. 12 times 1/3. It's basically 12 divided by 3, which is 4. So this is 4. And this equals, you would have 12 times 95/12. We know the 12s would cancel there. You're left with just 95. Okay, and then plus, you have 12 times 5/3 x. So 12 times 5/3 x. 12 cancels with 3 and gives me 4. 4 times 5 is 20. So this would be 20x. Okay, so now that we've cleared our fractions, let's just proceed into our normal procedure for solving a linear equation. Let's go ahead and subtract 4 away from each side of the equation. And also, let's go ahead and subtract 20x away from each side of the equation. So this is going to cancel, and this is going to cancel. Negative 6x minus 20x is negative 26x. And this equals 95 minus 4 is 91. So to solve this equation for x, I'm just going to divide both sides of the equation by negative 26, since negative 26 is what is multiplying x. Now, we will not get an integer or whole number here. We're going to end up with a fraction as an answer. So we're going to get x is equal to, if I think about 91 and negative 26, I know if I'm dividing here, I'm going to get a negative, right? Because positive over negative is negative. Now 91 is basically 7 times 13. So I could write this as 7 times 13. I could write negative 26 as negative 1 times 13 times 2. So we can all see that this 13 would cancel with this 13. You'd be left with 7 over negative 2, or you could just write negative 7 halves, however you want to do that. Essentially, you could also write this in decimal form as negative 3.5. But however you want to notate it, the answer is x equals negative 7 halves. Now, I'm not going to check this one in the interest of time, but if you wanted to, you could pause the video, go back up to the original equation, plug in a negative 7 halves for each occurrence of x, verify that the left and the right side are the same value. All right, so let's talk a little bit about how to clear an equation of decimals. This is a very, very simple process. And again, you don't have to do this. This is not one that's going to really save you a lot of time, especially if you have a calculator, okay? So remember that when you're multiplying by 10 or power of 10, such as 10 squared, 10 cubed, 10 to the 4th, 10 to the 5th, so on and so forth, this moves the decimal point one place to the right for each 0 in the power of 10. And remember also that if you have this notation, so 10 squared, the 2 there, that exponent on 10 tells me how many zeros I have. 10 squared is 100, it has 2 zeros. 10 cubed is 1,000, it has 3 zeros. 10 to the 4th power is 10,000, it has 4 zeros, right? So on and so forth. So if this guy right here is telling me that I have 10 squared, 2 zeros, I would just move my decimal point 2 places to the right if I multiplied by it. So if I had something like, let's say 3.68, and I multiplied by 10 squared, all I've got to do is take this decimal point here and move it 2 places to the right. This would give me an answer of 368, okay? So very easy to multiply by powers of 10, whether they're given as a whole number or they're given in exponential form, it's very easy to do. All right, so let's take a look at an example here. So we have negative 3.1x minus 1.1x, and this is equal to negative 2.2x minus 8. So the general idea here is to look at your equation, look at all the decimal numbers that you have involved. So what is the largest number of decimal places that you have on any given decimal number? So in this guy right here, this negative 3.1x, I have 1 decimal place. Again, that's places after the decimal point. Here I have 1 decimal place. Here I have 1 decimal place. And if I think about this as negative 8, or I could just think about it as subtracting away 8, however you want to think about that number as a whole number or as an integer, it's not a decimal number, right? You can put 0.0 if you want, but basically this 0 doesn't add any value. So this is really not a decimal number, so we don't even look at it. I'm going to erase this and just kind of look at these three numbers here. So the largest number of decimal places is just 1. So if I wanted to clear this equation of decimals, I could just multiply both sides of the equation by 10, and I would move all the decimal points one place to the right. I would have no more decimal numbers. So let's go ahead and do that. I would have 10 multiplied by negative 3.1x minus 1.1x, and then is equal to, over here I would have negative 2.2x minus 8, again multiplied by 10. So 10 times negative 3.1 would just be negative 31, right? Just move this one place to the right. Then my x comes along for the ride. Then minus 10 times 1.1 would be 11, right? Move this one place to the right. Then times x. So this left side just becomes negative 31x minus 11x. On the right, 10 times negative 2.2 would be negative 22. Again, just move this one place to the right. Then you've got times x, and then minus 10 times 8 is just 80, right? You can think about that as putting a decimal point there and just moving it one place to the right. So it's just 80. So now I have an equation that is decimal free, right? So all basically whole numbers or integers involved. So on the left, negative 31x minus 11x is going to be negative 42x. On the right, I just have negative 22x minus 80. Nothing I can really do to simplify there. To solve this, I'm just going to add 22x to each side of the equation. And what's going to happen is this is going to cancel. Negative 42x plus 22x is going to give me negative 20x. This will be equal to negative 80. If I've got negative 20 that's multiplying x, I can isolate x by dividing both sides by negative 20. Right? The coefficient of x, or what is multiplying x. So now I'm going to cancel this with this and say this is x is equal to negative 80 over negative 20 is 4. Okay, so that's going to be my solution. Again, if you want to stop and check, go back up and plug in a 4 for each occurrence of x, and you will see that you get the same value on the left as you do on the right. All right, let's take a look at one more of these. Pretty easy concept overall. So we've got negative 0.9x minus 59.76, and this is equal to negative 10.8 multiplied by the quantity x plus 8, and then minus 4.9x. So again, if you're clearing fractions or clearing decimals, and you have some parentheses involved, clear those first, and then go to your procedure. So I'm going to rewrite this as negative 0.9x minus 59.76, and this is equal to negative 10.8 times x is negative 10.8x, and then negative 10.8 multiplied by 8 is negative 86.4, so minus 86.4, and then minus 4.9x. So what I want to do is just multiply everything by the power of 10. That would clear all of the decimal numbers. Okay, so we want to make those into integers or whole numbers. So this has 1 decimal place, this has 2, this has 1, this has 1, and this has 1. So the largest number of decimal places occurs here with 2. So to clear that decimal, I need to multiply by 100, right? Because 100 has 2 zeros. I would move 2 places to the right, 1 for each 0. So I'm going to multiply both sides of the equation by 10 squared, or again, 100 as a whole number. So 10 squared multiplied by negative 0.9x minus 59.76, and this is equal to, over here, I'm going to do the same thing. So negative 10.8x minus 86.4 minus 4.9x, again, multiplied by 10 squared, or 100. So all I'm going to do for my multiplication here, it's very, very easy. Just moving each decimal point 2 places to the right. So this guy is going to go 1, 2 places to the right. So if you had 0.9, forget about the negative for a second, and I move this 2 places to the right, I'm going to end up with the number 090. The 0 in front of the 9 doesn't add any value. It's just 90. So what I'm going to end up with here, because it's negative, I'm going to have a negative 90 and then x. Then minus. This guy goes 2 places to the right. I get 5,976. Then over here, if I multiply 10 squared by each term, my negative 10.8x, I would have negative 10. This goes 1, and then a second place to the right, so negative 1,080x. Then minus, this would go 2 places to the right, so 8,640. And then minus, this goes 2 places to the right, so 490x. So now let's go ahead and just combine some like terms. On the left, I can't really do anything. So I'm just going to write negative 90x minus 5,976. On the right, negative 1080x minus 490x is going to give me negative 1570x, and then minus 8640. All right, let's scroll down, get some room going. So what I want to do now, I'm going to add 1570x to each side of the equation. And what's going to happen is this is going to cancel. And I'm going to add 5,976 to each side of the equation. So this is going to cancel. So negative 90x plus 1,570x is 1,480x. This equals negative 8,640 plus 5,976 is negative 2,664. All right, so the last thing I want to do is isolate my variable x. So I'm going to divide each side of the equation by 1,480. This is not going to be a whole number or an integer as an answer. Essentially, I know that it's going to be negative, right? X will be equal to something that's negative because I have a negative over a positive. If I factored each of these, I would find that we have a common factor of 296. So if I divide 2,664 by 296, I would get 9. So this would be negative 9 over. If I divided 1,480 by 296, I would get 5. So you get x equals negative 9/5. Or as a decimal number, you could say negative 1.8, right, if you did that division. So this would be my answer. Either one of those, you could write x equals negative 9/5 or x equals negative 1.8. And again, if you want to check, you go back up, you plug either of those in for x in the original equation, and you verify that the left and the right side are equal. In this lesson, we're going to review identifying types of equations. So in this short lesson, we're going to talk about the 3 types of equations that we're going to come across. In most cases, we're going to work with something known as conditional equations. So these equations are true under certain conditions, but false under others. So in the case of a linear equation of one variable, we have something like negative 3 times the quantity x plus 3 is equal to negative 13 minus x. So let's just solve this for x. We would simplify each side first. So negative 3 multiplied by x would be negative 3x. The negative 3 multiplied by 3 would be minus 9. This would be equal to, we have negative 13 minus x. Let's move all the variable terms to one side and all the numbers to the other. So I'm going to add x to each side of the equation. And I'm going to add 9 to each side of the equation. So what's going to happen is, this is going to cancel, and this is going to cancel. Negative 3x plus x is negative 2x. This is equal to negative 13 plus 9 is negative 4. So negative 2x is equal to negative 4. I can solve that by just dividing both sides of the equation by negative 2. And I get that x is equal to 2. Okay, so that's my solution. So for this equation, it's conditional, right? It's true if x equals 2, but it's false under any other circumstance. So let me prove this. If I plug in a 2 here and here, right, I'm just plugging in for x, I will get a true statement. So let's erase this. And we would have negative 3 multiplied by the quantity. 2 plus 3 is 5, so times 5. This is equal to negative 13 minus 2. So negative 3 times 5 is negative 15. And this should be equal to negative 13 minus 2, which is negative 15. So negative 15 equals negative 15. So yes, this is true. So right now, this is a true statement. So we're good to go. But that's when x equals 2. So what if I tried a different value for x? We would see that we get a false statement, right? So let me erase this. And let's suppose I chose the value of negative 2 for x. So negative 3 times, you'd have negative 2 plus 3, which is going to give me 1. This equals negative 13 minus a negative 2 is plus 2. So negative 3 times 1 is negative 3. Negative 13 plus 2 is negative 11. This is false. Negative 3 does not equal negative 11. So you can see that our equation is true when we replace the variable x with the correct value of 2, but false under any other circumstance. So again, this is the definition of a conditional equation. So the next type of equation that you're going to come across is known as a contradiction. So these are equations that don't have a solution. And we're going to have a lot of these throughout the course. So something like 3 times the quantity 3x minus 1 is equal to 9x plus 5. So 3 times 3x is 9x. And then minus 3 times 1 is 3. And this equals 9x plus 5. So what I'm looking at here is the fact that 9x is over here on the left and 9x is over here on the right. If you have the same value on each side of an equation, you can just get rid of it. Why do I say that? Well, look at what I can do. I could subtract 9x away from each side. And what's going to happen is it cancels here and it cancels here. So it's just gone. What I'm left with is nonsense. -3 equals 5. That is false. So if you go through this process of solving an equation and you're left with nonsense, something like a false statement like -3 equals 5, you have a contradiction. So in this particular case, you would say that there's no solution. You could put no solution. Your book might show the symbol for the null or empty set. So when you think about sets, if your set contains no elements, right? If you had no solution, you wouldn't have any elements in the solution set. The way you notate that is with this symbol here. So this means no solution, if you see it in your book. Okay, no solution. You might also see empty set braces. This is probably less popular, but you might see that as well. What you don't want to do is combine the two. You don't want to use set braces with this symbol inside. That is incorrect. Okay, and for that, we'll talk about that when we get to set theory. All right, let's take a look at something else. So we also have an equation that's known as an identity. So -2 plus 2x is equal to -2 times the quantity 1 minus x. All right, so what do we do here? So we have -2 plus 2x is equal to -2 times 1 is -2, and then -2 times -x is plus 2x. So you'll notice that you have the exact same algebraic expression on each side of the equation. Two ways you can think about this. The first way is, no matter what I plug in for x, it doesn't matter what value it is, I'm doing the same thing to it on each side, so I'm always going to get the same result. It's always going to be true for all real numbers, no matter what I do. The other way you could think about this is, I could go through the process of solving it, and I could say, okay, well, I could subtract 2x away from each side. So this is going to be gone, right? That's gone. I could add 2 to each side. So now this is going to be gone. So what am I left with? I'm left with 0 is equal to 0, which is true. So if in the process of solving your equation, you end up with something that's just true always, well, then you have an identity. Okay, you have an identity. Okay, and an identity is true for all real numbers. So you can say all real numbers. Okay, that's going to be your solution. In this lesson, we want to review solving proportion equations. So in this lesson, we're going to talk a little bit about how to solve proportion equations. It's a pretty simple concept. Again, it's something that most of you already know how to do. We're going to start out by just talking about the equality test for fractions. So essentially, you can tell if two fractions are equal by basically checking the cross products. So if I have something like 1/4 and 3/12, I can tell if they're equal by multiplying the denominator of one fraction by the numerator of the other. So 4 times 3 is 12. And then doing the same thing over here. So the denominator of one fraction by the numerator of the other. 12 times 1 is 12. If you get the same result in each case, then you have a proportion, right? You have two fractions or two ratios, or it could be two rates that are equal in value. So that's a proportion. So these are equal. I could say 1/4 is equal to 3/12. You can also see that that's equal because if I multiply 1 by 3, I get 3. If I multiply 4 by 3, I get 12. So essentially all I really did here was take 1/4, multiply it by 3 over 3, which is the complicated form of 1, and I got 3/12. Okay, so of course 1/4 and 3/12 are equal. All right, let's look at another one. So we have 9/14 and we have 20/27. So again, we can check this guy by just cross multiplying. So I can multiply 14 times 20. It's pretty easy to do. You multiply 14 times 2, you get 28. You put a 0 at the end, you get 280. And I'd multiply 27 times 9, which would be 243. So these two values, these two cross products are not equal. So these two fractions are not equal. So we can say 9/14 is not equal to 20/27. So let's talk a little bit about solving proportion equations. We already reviewed previously how to solve equations with fractions. So one way you could solve this if you wanted to, you could multiply both sides of the equation by the LCD of all the denominators. But a quicker way, when you just have one fraction equal to another, is just to cross multiply, right, to set everything up. So in other words, if I have x over 38 is equal to 2 over 19, all I have to do is cross multiply, right? Because if we have two fractions that are equal, the cross product should be equal. So that means that 38 times 2, which is 76, should be equal to 19 times x, or 19x. So now all I got to do is solve this in one step, divide both sides by 19, and I get x is equal to 4. You can check that pretty easily. Just plug in a 4 for x there. You would have 4 over 38 is equal to 2 over 19. Of course this is true. If I take 2 and I multiply by 2, I get 4. If I take 19 and I multiply by 2, I get 38. So essentially, it's like I did this. I took 2 over 19 and I multiplied it by 2 over 2, and I got 4 over 38, right? So x is going to be 4 in this case. What about something like x over 60 is equal to negative 7 over 15? Again, we can just set this up by cross multiplying. So 15 times x is 15x. This is equal to negative 7 times 60. Negative 7 times 6 is negative 42. And then just put a 0 at the end, so it's negative 420. And now we just want to divide both sides by 15 so that I can isolate my variable x. And so what am I going to get? Negative 420 divided by 15 would be negative 28. So x is equal to negative 28. Okay? And of course, you can check that. You could plug in a negative 28 for x there. So you would have negative 28 over 60 is equal to negative 7 over 15. Again, you can kind of eyeball this and see if I multiply negative 7 times 4, I get negative 28. If I multiply 15 by 4, I get 60. Okay? So we can see that that is correct, right? Negative 28 over 60 would reduce to negative 7 over 15. So those two are equal. All right, let's take a look at another one. So we have 9 over x minus 7 is equal to 6 over x. So I'm going to cross multiply here just like I normally would, but I've got to be careful. 6 is multiplying x minus 7. It's multiplying that quantity. So I would have 6 times the quantity x minus 7. The 6 has to multiply the x, and it's got to multiply the negative 7. A common mistake is just to put 6x minus 7 like that. Okay, that's wrong. The 6 has to multiply both of those terms. So 6 times the quantity x minus 7 is equal to x times 9, or 9x. So I'm just going to kind of clean this up on the left. 6 times x is 6x. And then minus 6 times 7 is 42. This equals 9x. Let me subtract 9x away from each side of the equation. And let me add 42 to both sides of the equation. So what we're going to have here is that this cancels and this cancels. And let me just kind of bring this up here to the top. We're going to say 6x minus 9x is negative 3x. And this is equal to, we're going to say 42. If we divide both sides of the equation by negative 3, we know we would have x is equal to 42 over negative 3. We know that's negative. And 42 over 3 is 14. So this would be negative 14 as our answer. Now, you can check this if you want. Let me erase everything. We'll plug in and make sure the left and the right sides are equal. Let me just kind of scooch this up. And I'm going to plug in a negative 14 here and here. So what you'd have is 9 over, you have negative 14 minus 7. Negative 14 minus 7 would be negative 21. Now before I go any further, I know I can simplify this. Each is divisible by 3. 9 divided by 3 is going to be 3. Negative 21 divided by 3 is going to be negative 7. So let's just write this as negative 3/7. So that's what I'm looking for here. If I plug in a negative 14, I'd have 6 over negative 14. So each is divisible by 2. If I divide 6 by 2, I get 3. If I divide 14 by 2, I get 7. And of course, it's negative there. So let me just throw that out in front. You see that you get negative 3/7 is equal to negative 3/7. Okay? So we get the same value on the left as we get on the right. So we can say x equals negative 14 is our correct solution. All right, let's take a look at another. So we have 5 times the quantity 3x plus 1 over 7 is equal to 9x minus 3 over 3. So again, I'm just going to set this up by cross multiplying. So 7 multiplies the quantity 9x minus 3. So 7 times the quantity, again in parentheses, 9x minus 3, is equal to 3 multiplies. In this case, it's easier just to multiply the 3 by the 5 first. So 3 times 5 is 15, and then times this whole quantity, 3x plus 1. So now let me simplify each side. 7 times 9x is 63x, and then minus 7 times 3 is 21. This equals 15 times 3x is 45x, and then 15 times 1 is 15. So let me subtract 45x away from each side of the equation. And what's going to happen is this will cancel. Let me add 21 to both sides of the equation. And so this guy right here is going to cancel. So 63x minus 45x is going to give me 18x. And this equals 15 plus 21 is going to be 36. So let me erase all this. I don't need any of this anymore. All I'm going to do is divide both sides of the equation by 18 now so that I can isolate x. So let me drag this up here. I'm going to divide both sides by 18. So again, that I can isolate x. 18 over 18 is 1, so I just have x is equal to 36 over 18 is 2. Okay, so that's my solution. Now again, I like to check things. I think you should too. Plug in a 2 for x here, and make sure you get a true statement. So if I had 5 times the quantity, 3 times 2 is 6, 6 plus 1 is 7. So this is 5 times 7 over 7. 7 over 7 is 1, so this is basically 5 on the left. So 9 times 2 is 18. 18 minus 3 is 15, so you'd have 15 over 3, which is 5 as well. So you get 5 equals 5. So x equals 2 is the correct solution here. All right, let's take a look at one more of these, and then we'll just kind of look at some word problems. So we have negative 12x plus 5 over 2 is equal to 7 times the quantity x minus 9 minus 3 over negative 11. So again, we set it up in the usual way. We're going to cross multiply. We've got to be careful here. 2 is going to multiply by this numerator. You've got to multiply 2 by each part. So you can kind of set this up using brackets. So 2 times. Inside of brackets, I'll just put my numerator. So 7 times the quantity x minus 9, and then minus 3. This equals, you're going to set this part up. So negative 11 times, you've got your quantity here, your negative 12x plus your 5. So you can go through here and you can distribute this to each part, or you can clean up what's inside and multiply by 2, whatever you want to do. 2 is going to multiply by 7 times the quantity x minus 9. That's just 14 times the quantity x minus 9. Then minus 2 times 3 is just 6. And this equals negative 11 times negative 12x is 132x. Then negative 11 times 5 is minus 55. Now, on the left-hand side, 14 times x is 14x. And then minus 14 times 9 is 126. Okay, then minus another 6. So if you had negative 126 minus 6, that would be negative 132. So that's my left side, 14x minus 132. And this equals, on the right side, you've got 132x minus 55. Okay, so let's go ahead and solve this guy. I'm going to add 132 to each side of the equation. So we know that this is going to cancel. Then I'm going to subtract 132x away from each side of the equation. So this is going to cancel. So 14x minus 132x is negative 118x. And this equals, you've got negative 55 plus 132, which is 77. So let's go ahead and finish this guy up. Let's divide each part by negative 118. And this will cancel with this. You'll have x is equal to negative 77 over 118. Now, is this something that I can simplify? 77 is 7 times 11. 7 is prime, 11 is prime. 118 is not divisible by 11, and it's also not divisible by 7. So this is as simple as you can make it. So x is going to be negative 77 over 118. Now this is something you can check just like we have throughout this lesson. But because it's so tedious, and in the interest of time, I'm not going to check it. But if you want to, you can go back, you can pause the video, plug in a negative 77 over 118 for each occurrence of x, and you'll see that the left and the right side are equal. All right, so now let's turn to some word problems. And these are typical examples that you would see if you were in a section where you're talking about solving proportions. So we have that Jacob drove his car 300 miles using 20 gallons of gas. How many gallons of gas would it take for Jacob to travel 1,200 miles? So this is a very easy problem to set up and solve. Essentially what we want to do is take kind of the first information they give us and set up a unit rate, right? So it says Jacob drove his car 300 miles using 20 gallons of gas. So we have 300 miles per 20 gallons of gas. And you can write of gas if you want. I'm just going to leave 20 gallons in the denominator. And so what I would want to do, or the easiest thing to do here, is just to get a unit rate. So 300, the number in the numerator, divided by 20, the number in the denominator, would be 15. So I could basically say that it's 15 miles per 1 gallon of gas. Okay, so that's a unit rate. Now, with the second part, we're asked a question. how many gallons of gas would it take for Jacob to travel 1,200 miles? So again, because the miles per gallon here, we're going to assume it stays the same, I can set up a proportion equation. So I can say this is equal to, the miles are going to be in the numerator, so I'm going to put 1,200 miles in my numerator over here, and this is over. The unknown here is the gallons of gas that would be used. So since gallons, or gallon in this case, is in the denominator, I'm going to just use x as a variable to represent the unknown number, and then my units would be gallons. Okay, so gallons. So once you've got this set up, it's very easy. You're just going to cross multiply. If your units are the same in the numerator, which in this case it's miles and miles, and your units are the same in the denominator, so you have gallon and gallons, same units, one singular, one's plural, you're good to just cross multiply with the number parts, or in this case it's going to be a variable. So I would take 1 and multiply it by 1,200, so that's 1,200, and then set this equal to 15 times x, or just 15x. So all I need to do now is just solve the equation for x, and I can really quickly do that by just dividing both sides of the equation by 15. So what is 1,200 divided by 15? Well, that's going to give me 80, right? So I would get that x is equal to 80, and x here represents the number of gallons it's going to take for him to go 1,200 miles, okay? So let's erase everything, and we can just answer this. How many gallons of gas would it take for Jacob to travel 1,200 miles? We'll say it would take 80 gallons of gasoline. All right, let's take a look at one more of these. So the distance between Smithland and Creek Falls is 2,400 miles. On a given wall map, this distance is scaled down to 4.8 feet. On the same wall map, how many feet would be between Port Charles and River Ridge, two cities which are 4,000 miles apart? So again, another easy one. Essentially, it tells us that we have this given wall map, and basically the scale is proportional, right? So it takes a certain distance in the real world, and it scales it down. So between Smithland and Creek Falls, it's 2,400 miles. So we're going to say that 2,400 miles over, on this wall map, it's scaled down to 4.8 feet. So 4.8 feet. And we're just going to set up a proportion. Again, on the same wall map, we have this city, Port Charles and River Ridge. They're 4,000 miles apart, but we don't know how this is going to be expressed on our map. So to figure this out, we're just going to put 4,000 miles here in the numerator, because that's their distance in real life, just like we had over here. And this will be over x feet. Okay, this is going to be the kind of distance on the map. How many feet will it be? So to figure this out, we're just going to cross multiply. We're going to take 4.8, multiply it by 4,000, which would give us 19,200. We set this equal to x times 2,400, so 2,400x. And to solve this guy for x, I'm just going to divide both sides of the equation by 2,400. If I divide 19,200 by 2,400, I'm going to get 8, right? So x here is going to be equal to 8. So I can erase this. Got all my information now. Instead of saying x feet, this would really be 8 feet. So I can go back and just answer this. We would say they would be 8 feet apart on the wall map. In this lesson, we want to review solving literal equations. So far in our course, we've only looked at equations with one unique variable. So something like 2x minus 5 is equal to 11. We know if we solve this, we get x equals some number, right? So if I would quickly solve this, I could add 5 to each side of the equation. We know that this is going to cancel. We would have 2x is equal to 11 plus 5 is 16. To isolate x here, we just need to divide both sides by 2. And we would find that x is equal to 16 divided by 2 is 8. So you see you have x equals some number there, okay? When you're working with just one unique variable, in most cases you get a variable equals some number. But when we talk about literal equations, we're talking about equations with more than one unique variable. So a lot of times we will work with more than one unique variable, especially as we get further along into algebra. So if we see something like, let's say 2x plus, let's say 5y, and let's go ahead and say this is equal to 20. Now, I can't get this in terms of a variable equals just some number because I have two variables involved. But I can still solve for one of the variables. I can choose to solve for x. I can also choose to solve for y. So if I wanted to just solve for x, what would I do? Well, if I want to isolate this guy, the first thing I always want to do is isolate the variable term that contains the variable that I'm trying to isolate. So I would start by just isolating the 2x. So to do that, I would subtract 5y away from each side of the equation. So I would have just 2x on the left. I know that this would cancel over here. 5y minus 5y, that's 0. So this equals, now I'll have my minus 5y and then plus my 20. Now, how can I get x by itself? Well, I just have the 2 that's multiplying x. So no change here. I just divide both sides of the equation by 2. But now over here, I'm dividing this whole expression here. I have my negative 5y plus 20. The whole thing's divided by 2. And let me scroll down and get a little room going. So over here, 2 over 2 is 1. So I just have x. And this is equal to, you have your negative 5y plus 20 over 2. Now, there's different ways to write that. You could split that up as negative 5y over 2 plus 20 over 2. So I could also say x is equal to negative 5y over 2 plus 20 over 2. And of course, 20 over 2 is 10. So you could also write it like this. Either answer is acceptable, okay? But I'm just showing you that you can write things in terms of one variable. So I could say x equals something. I can also solve this equation for y. So if I want to solve for y, again, the first thing I want to do is isolate the variable term with y involved. So because 2x is being added to this 5y, I just subtract 2x away from each side of the equation. Very, very easy. This is going to cancel. We would have 5y is equal to, you have your negative 2x, and then plus your 20. And of course, to get y by itself, I'm just going to divide both sides of the equation by 5. And so you'd have y is equal to, you have your negative 2x plus 20 over 5. And again, you could write that differently if you want. You can split that up and say this is y is equal to negative 2x over 5 plus 20 over 5. And 20 over 5 is just 4. So either way you want to write it, both these answers would be acceptable. We're just showing you that you can solve for one of the variables, right? So now this equation is in terms of y. Y equals some expression. Before we looked at x equals some expression. So when you get more than one unique variable involved, you're not going to have a variable equals some number. You're going to have a variable equals some expression. So normally when we talk about solving literal equations, we're talking about taking a formula and putting it in terms of one of the variables. So this is very useful when we look at application problems, right? So word problems. So we're just going to go through a few typical problems that you would see. And basically, we just need to understand how to solve something for a specified variable. So the first formula we're going to look at is for the perimeter of a rectangle. So if you have a rectangle, you have a length here and a length here. So on the top and the bottom. And then on the sides, you have your width, right? So length is labeled with L, width is labeled with W, okay? So the perimeter, or the distance around a rectangle, is given as 2 times the length plus 2 times the width, okay? So what we want to do here is just solve for W and then also solve for L. Right now you'll notice that it's solved for P, or put in terms of P, because P is isolated on one side of the equation, right? You have P equals some expression. In this case, that expression is 2L plus 2W. All right, so to solve for L, let me just rewrite P equals 2L plus 2W. And if I want to solve for L, again, I just want to start by isolating the 2L, right? Always start by isolating the variable term, which contains the variable you want to isolate. So all I need to do is subtract 2W away from each side of the equation. So I'm going to have that P minus 2W is equal to 2L. And if I want to isolate L there, what's being done to it? It's being multiplied by 2. So just divide both sides of the equation by 2. And I'm going to flip this around. So 2's cancel there. You get L is equal to P minus 2W over 2. Okay, so this is in terms of L now. So if I wanted to put this in terms of W, we'd use the same thought process. So I want to begin by isolating the term with the W involved. So to do that, I would just subtract 2L away from each side of the equation. So I would have that P minus 2L is equal to 2W. And again, to isolate W, I just divide both sides of the equation by 2. Okay, very, very easy. 2 over 2 is 1, so you get W is equal to. So W is equal to, you get P minus 2L over 2. And all I'm doing here is I'm just switching the variable to the left. That's perfectly legal, right? If I wrote this here as W on the right, and this is equal to P minus 2L over 2, I can switch this around and say this is W is equal to P minus 2L over 2. Okay, it's the same thing. I just like my variable on the left. I don't like it on the right, but you can write it either way. They're both acceptable. All right, let's take a look at another formula from geometry. So we have the area of a trapezoid here. So A, which stands for area, is equal to H, which stands for height. That's this guy right here. Times the quantity. You have an uppercase B, which is down here. That's the lower base. Then plus a lowercase b, which is up here. That's your upper base. So then we divide this by 2. So what if I wanted to solve this guy for uppercase b? What could I do? Well, remember, you want to isolate the variable term with that involved first. Right now, it's wrapped inside of a set of parentheses. So one thing I could do is just remove the parentheses with my distributive property to kind of get things started. So we would have A is equal to, you have H multiplied by, again, uppercase b plus lowercase b, and this is over 2. So I have A is equal to, H times uppercase b is H times uppercase b, then plus H times lowercase b is H times lowercase b, and this is over 2. Now, if I want to isolate, again, this term here to start, what I'm going to do is just clear my denominator. I can easily do that by multiplying both sides of the equation by 2. So this would cancel. Let me kind of go up here. I would have 2a is equal to, you would have H times uppercase b plus H times lowercase b. Okay, so what do I do from here? Well, I want to isolate, again, this term right here because it's got my uppercase b involved. So all I'm going to do is just subtract H times lowercase b away from each side of the equation. And so let me kind of scroll down and get some room going. I'm going to have 2a minus H times lowercase b is equal to H times uppercase b. So to get uppercase b by itself, I'm just going to divide both sides of the equation by H, and this would cancel. So let me write my answer over here so it's out of the way. I have uppercase b is equal to, you have 2a minus H times lowercase b over H. Okay, so that's just solving this for uppercase b. If you wanted to solve it for lowercase b or you wanted to solve it for H, you would go through the same thought process. So let's go ahead and solve this for H. Let's erase everything. So again, we'll rewrite this formula down here. Area, or A, is equal to, you have H times the quantity, uppercase b plus lowercase b, and this is over 2. How can I get H by itself? Well, before I go through and use my distributive property, let's just clear the denominator. Let's multiply this side by 2 and this side by 2. So this cancels. So now I have 2a is equal to, I have H, again, multiplied by the quantity, big B or uppercase b plus small b or lowercase b. Now, if I want H by itself, what can I do? H is being multiplied by something here. Erase this and imagine that you had 4H and you wanted H by itself. You would just divide both sides by 4, right? What's multiplying H? Well, let's go back now. This quantity here is multiplying H. So all I've got to do is just divide both sides of the equation by that quantity. Big B plus little b. So big B plus little b. And I've got my answer, right? This is going to cancel. And so what I'm left with here, I'm going to put H is equal to, you have 2a over bigger B or capital B plus lower b or smaller b, okay? So now it's in terms of H. All right, let's go ahead and wrap up this problem by solving the equation for the lowercase b now. And again, the idea is always the same. If I'm solving for the lowercase b, I just want lowercase b on one side of the equation, and I want an expression on the other. Okay, so very, very easy. So we have that a is equal to, we've got h multiplied by the quantity. You've got your uppercase b plus your lowercase b, and this is over 2. And let's get some room going here. Now, there's many ways to start this problem. You can start by using your distributive property to remove the parentheses, because ultimately you need to get to that b, and it's inside of parentheses right now, so that's one thing you can do. Another thing you can do is you can clear the denominator first. So we can do that, and let's just start by that. So we'll go ahead and cancel this with this, and we'll do 2a is equal to, we've got h times the quantity, you've got your uppercase b plus your lowercase b. Now, you can use your distributive property to remove parentheses. That's fine, that's one way to do it. Or another way, and probably a faster way, you can just divide both sides of the equation by h, right? Because if you divide both sides of the equation by h, then you can go ahead and remove those parentheses, and you'll have access to this lowercase b here. So I'll have 2a over h on the left, and this is equal to, now I just have the capital letter b plus the lowercase b on the right, okay? So to solve for the lowercase b now is very, very easy. I just have this capital letter b that's being added to it, so I'm just going to subtract the capital letter b away from each side of the equation, and so I'm going to end up with 2a over h minus the capital letter b, and this is equal to the lowercase b, okay? And if you like the variable on the left, like I do, you can rewrite this. You can say lowercase b is equal to 2a over h, and then minus uppercase b. Now you'll notice that we don't have a common denominator here. If we want a common denominator, we can get one. We can just multiply this by h over h. If we would have used the distributive property, we would have gotten one. So this is just a matter of personal preference. It's the same answer either way. So I can write this as lowercase b is equal to 2a minus uppercase b times h all over the common denominator of h. Or again, it's the same thing if you say lowercase b is equal to 2a over h minus uppercase b. All right, let's look at some other problems. So suppose I wanted to solve this for just x. So z times the quantity ax minus bd plus nq equals nx minus a. How can I solve this for x? I have an x here, and I have an x here. Well, if you get this scenario, you've got to get all the terms with an x involved to one side and everything else to the other. So let's go ahead and distribute this z to each term inside the parentheses. So you would have zax minus zbd, then plus nq, and this is equal to nx, and then minus a. So I want this term and this term, because they each have an x involved, on one side of the equation. I want everything else on the other. So what I'm going to do is I'm going to subtract nx away from each side of the equation, and I'm going to add zbd to each side of the equation, and then I'm going to subtract nq away from each side of the equation. Okay, so a lot of stuff on the screen here. Let's go through this. So this is gone. I've canceled it. And this is gone. I've canceled it. So on the left, I'm going to have zax minus nx. Then this will be equal to, on the right, this is going to cancel. So I'll just have negative a plus zbd minus nq. Let me make that q a little bit better. Okay, so how can I solve this for x? A lot of you, if you see this, will be perplexed. What can I do here? Well, think about this if you had something like 6x minus 4x. We know we can combine like terms there, but why can we do that? Well, because of the distributive property. I can pull the x out, and I can say this is 6 minus 4 inside, so this becomes x times 2, or 2x. If I use the same thought process here, I can pull my x out because it's common to each, right? So if I pull that out, inside the parentheses I would have za minus n. Now I can't combine those, but that's okay. You'll see in a minute I can just divide by that because that's what's multiplying x. And this is equal to, you have your negative a plus your zbd, and then minus your nq. Now, again, this is multiplying x. So it's just like if I had 4x is equal to 20. If 4 is multiplying x, I can divide both sides of the equation by 4 so that x is equal to 5. Same thought process here. All I want to do is divide both sides of the equation by what's multiplying x. So it's the quantity ZA minus N, and I'm going to divide by that over here as well. So ZA minus N. And it looks messy, but this is what we need to do when we have a lot of variables involved. So I've solved this for x now because this is going to cancel. You have x is equal to, you have your negative a plus your zbd, then minus your nq over, you have your za, and then minus n. All right, let's go ahead and take a look at another one. So we have 5x minus the quantity 2q plus d is equal to a times the quantity x plus 1. So we want to solve this for x. And again, the idea here is if I want to solve it for x, I've got to first get all the variable terms with x involved on one side and everything else on the other. So because I have an x here wrapped inside of some parentheses, let's go ahead and use our distributive property, get everything simplified. So we have 5x. I have this negative out in front of these parentheses. So again, you can think about this as plus negative 1. The negative 1 would multiply by each term. So you'd have minus 2q and then minus d. And this equals, the a is going to multiply by each term. So ax and then plus a. Okay. So I want all my, again, terms with an x involved on one side. So let's go ahead and subtract ax away from each side of the equation. And let's add 2q to each side of the equation. And let's add d to each side of the equation. Okay? So this would cancel here. This would cancel here. And this would cancel here. So on the left-hand side, I've got 5x minus ax. And this is equal to, on the right-hand side, I've got a plus 2q plus d. All right. So now, what do I have here on the left? How can I isolate x? Well, again, I think about the process I used to combine like terms. If I have 5x minus, let's say, 6x, well, I can factor out the x there, and inside the parentheses, I would have 5 minus 6. We know 5 minus 6 is negative 1, so this is negative 1x. Well, here I can basically, again, do the same thing. I can factor out the x because it's common to each. So I can have x times the quantity 5 minus a. This is equal to a plus 2q plus d. Since this quantity 5 minus a is multiplying x, to get x by itself, I just divide both sides by that quantity. And I'll have x by itself. So I will have x is equal to, we'll have a plus 2q plus d over your 5 minus a. In this lesson, we want to review solving linear inequalities in one variable. So in the traditional sense, when we think about an inequality, we're thinking about a statement that two algebraic expressions are not equal in value. So something like 6 is less than 12 is a way to notate that 6 is a smaller number than 12. Or something like negative 4 is greater than negative 11 is a way to notate that negative 4 is larger, or you could say greater than negative 11. So when we work with inequalities, we have strict inequalities and we have non-strict inequalities. So strict inequalities, you have strictly less than and strictly greater than. With non-strict inequalities, which we'll see in a moment, you have less than or equal to, and then you have greater than or equal to, so you're allowing for the possibility of equality. So when we have an inequality with a variable involved, we need to understand interval notation, and we need to also understand how to graph an interval on the number line. So if we see something like x is greater than 5, how could we notate this on the number line? Well, first let's think about x equals 5. If x equals 5, then x can only be one value, it can only be 5. So on the number line, I could just put a dot there, right? A filled in circle, however you want to think about that. But if x is greater than 5, I don't want to go through and put a dot at every possibility, right? Because it's anything larger than 5. So it could be 6, it could be 7, it could be 8, it could be 9, it could be 2 million. So I want to basically shade all of these. And I would just shade the number line, and I would shade that arrow to say this continues forever. But I've got to have a point known as a boundary, okay? A boundary is what separates the solution region from the non-solution region. So over here, this is my solution region, okay? Anything on the right side of 5 satisfies this inequality. So if I took 6 and plugged it in, 6 is greater than 5, that's true. Okay, that's true. If I took 1 million and plugged it in, 1 million is greater than 5, that's true. Then anything on the left of 5 is in the non-solution region, right? Because it wouldn't work. If I took a 3, for example, and I plugged it in, is 3 greater than 5? No, this is false. Okay, this is false. So 5 itself is our boundary. It's where it separates the solution region from the non-solution region. So at that point, you either want to use a parenthesis or a bracket. You use a parenthesis when it's not included, and you use a bracket when it is included. Okay? So in this case, it's not included because we have a strict inequality. So what we want to do, we want to put a parenthesis facing in the direction of the solution region. So this is how you would graphically notate that x is greater than 5. 5 is not included, that's our boundary, but anything larger than 5 is included, and that's why it's shaded. Now, some of you will see a different notation. At 5, you may see an open circle to show that 5 is not included. So you might see something like this, and then everything is shaded to the right. And that's okay too. No problem there. It's just a different way to notate it. In this course, we're basically going to stick to this. So we're going to put our parenthesis here and then shade everything to the right. But feel free to do it either way. Now, you also need to think about interval notation. And it basically follows the same concept as we just looked at with graphing. So you're going to think about your smallest value, and you're going to think about your largest value. And you're going to separate them with a comma. Now, in this particular case, you don't really have a smallest value, right? Because if you think about it, 5 is your boundary, but anything larger than 5 works. So 5.00000001 works, or 5 point, you can extend a million zeros and then put a 1, that works. So for the smallest value, we just put 5, because that's as close as we can really get. And then we're going to put a parenthesis to the left of that to say that 5 is not included, right? So this just means not included. Not included. But we know automatically that anything larger than 5 would be included, okay? Then we put a comma, and then our largest value, again, because there is none, we use infinity. This is just a concept. So we put our infinity symbol to say this is going to continue forever in the right direction. You always use a parenthesis with infinity, okay? So again, not included. So 5, comma, infinity with a parenthesis next to each. So this is graphically, and this is with interval notation. Now let's look at a less than. So x is less than -3. So again, x can be any value that's less than or to the left of -3. So -3 is my boundary. My solution region is to the left of -3, so I want to shade everything to the left of -3. So I'm going to shade this arrow and all of this to -3. And at my boundary, I'm just going to put a parenthesis facing to the left, okay, to show that -3 is not included. But again, because I've shaded to the left, everything that's less than -3 would be. In interval notation, it's the same concept. We're going to put a -infinity here to represent our smallest value because there is none. I always use a parenthesis with either -infinity or positive infinity. Then comma, I'm going to put -3 for my largest value. And again, because that's not actually my largest value, because it's not included, I'm going to put a parenthesis there. So you have -infinity, you have -3, you have a parenthesis next to each. Let's quickly look at non-strict inequalities. So you have less than or equal to and greater than or equal to. So these allow for the possibility of equality. So x now is greater than or equal to 5. So it's basically the same thing, but we allow for 5 to be part of the solution. So I use a bracket when that occurs. So all I need to do here is just put a bracket at 5 and shade everything to the right. And the bracket just tells me that 5 is included. Now, in interval notation, I can put a bracket of 5, comma, infinity. And again, the bracket just says that 5 is included. Okay, it's part of the solution now. And it's worth noting here that we also have another notation that we can use for this. Some textbooks, when you have a non-strict inequality, will put a filled-in circle at the boundary. So to include 5, instead of using a bracket, they'll put a filled-in circle, okay? So the filled in circle means it's included, and then we would shade everything to the right like this. But again, in this course, we're going to stick to using a bracket. So I'm going to put a bracket at 5 and just shade everything to the right. You can use any method you want. They're both the same, just different ways to show the same concept. Then for x is less than or equal to -3, again, I'm going to use a bracket because -3 is part of my solution. So I'm going to put a bracket at -3 facing to the left and just shade everything to the left here. Okay. In interval notation, I've still got my negative infinity, and then comma, I'll have a -3 with a bracket next to it. So -3 is included, so that's why I have my bracket. With positive or negative infinity, I always use a parenthesis. All right, so now let's move into what a linear inequality in one variable is going to look like. So we have stuff like ax plus b is less than c, where a does not equal 0. So essentially here, this is generic. We have a, b, and c, which are any real number, with the exception that a cannot be 0. And we could basically replace this less than with a greater than, or a less than or equal to, or greater than or equal to. So something like 3x plus 5 is greater than 11, or something like -7x plus 2 is less than or equal to 16. So essentially exactly what we saw when we solved linear equations in one variable, with the exception of we're flipping the equality sign into an inequality sign. All right, so suppose we came across an inequality such as x minus 11 is less than -14. So before we solve this, let's think about an equation. So x minus 11 is equal to -14. How could we solve this? We know about the addition property of equality. That tells us we can add or subtract the same number to, or in the case of subtraction from, both sides of an equation and not change the solution. So to isolate x here, all I need to do is add 11 to both sides of the equation, right? Because I'm subtracting away 11 here. If I add 11, I'm going to basically cancel this with this, and I'm left with just x. So here I would have x is equal to -14 plus 11 is -3. So we can use the same process when we solve inequalities. So let's erase this, and let's write our problem down here. So we have x minus 11 is less than -14. So when it's used with inequalities, it's called the addition property of inequality. And essentially, this property allows us to add or subtract the same value to, or in the case of subtraction from, both sides of an inequality without changing the solution set. Okay? So I'm using the same technique here. I want to isolate x. And since I'm subtracting 11 away from x, I just add 11 to both sides of the inequality. And again, this cancels, and I get x is less than -3. Okay, very, very easy. So we would want to notate our solution, again, using interval notation and then graphically. So to notate this in interval notation, I know that I would put a parenthesis and a negative infinity, and then comma, I would have a -3 there. And again, because -3 is not included, I'd put a parenthesis. So graphically, I would find -3, so that's right here. I'd put my parenthesis in, and then I would just shade everything to the left. Okay, so all of this going to the left, including the arrow. All right, let's take a look at another one. So we have x plus 9 is greater than or equal to 15. So again, I want to get x by itself. I always want to isolate x on one side of the inequality. So to do that, I can just subtract 9 away from each side of the inequality. And this guy right here is going to cancel. I'll have x is greater than or equal to 15 minus 9 is 6. So again, I've got a greater than or equal to there, so I want to use a bracket. So let's find 6 on our number line. We want to put a bracket to show that it's included. And then we're going to shade everything to the right. That's our solution region. Okay. In interval notation, I would put a bracket and then put a 6. This would be my smallest number. And then comma, you would have infinity. That would represent the largest number, right? There is none. This continues forever. So now let's talk a little bit about the multiplication property of inequality. So you know that we have a multiplication property of equality that we use with equations. So if I had something like 5x is equal to 15, we know we can multiply or divide both sides of an equation by the same non-zero number and not change the solution. So since 5 is multiplying x here, I can divide both sides of the equation by 5, and I get that x is equal to 3, right? Very easy. You have the same property with inequalities, but you have an exception here that you really need to pay attention to. With the multiplication property of inequality, you can essentially multiply both sides of an inequality by the same positive number, okay, positive number, and not change the solution. Okay, you can also divide both sides of an inequality by the same positive number and not change the solution. What about negative numbers? Well, we'll talk about that in a minute. So let's just look at this inequality real quick. So 5x is greater than 15. We know we want to isolate x. 5 is multiplying x, so we can go ahead and divide both sides of the inequality by 5, and we would get that x is greater than 3. In interval notation, we would put a parenthesis, a 3, and then we would have an infinity symbol and a parenthesis. Okay. Graphically, I could put a parenthesis at 3 to show that it's not included. 3 is the boundary, and we're going to shade everything to the right. Let's take a look at another one. So now we have 7x is less than or equal to 49. So 7x is less than or equal to 49. Again, if I want to isolate x, I can just divide both sides of the inequality by 7. And I'll get x is less than or equal to 7. Okay, very, very easy. In interval notation, you would have a negative infinity, and you would have a 7 here. But again, because this is less than or equal to, next to the 7, I put a bracket, okay, because it's included. So graphically, I would look at 7, I would put a bracket, and then I would shade everything to the left here. This is my solution region. So all of this. All right, so let's talk about the case where you're multiplying or dividing an inequality by a negative number. So for this, I want to just show you real fast what happens when you multiply an inequality by a negative number. All right, so suppose we started out with something like 3 is less than 7. We know at this point that this is a true statement. 3 is less than 7. If I multiply both sides of this guy by positive 2, so let's say I multiply by 2 over here, and I multiply by 2 over here. So 2 times 3 is 6. 7 times 2 is 14. 6 is less than 14. That's still true. Okay, so nothing really changed there. I still have a true statement. But let's say I multiplied both sides by negative 2. What would happen? Well, I'd have negative 6 over here, and I would have negative 14 over here. Now this is false. Now this is false. So what happened here? Well, the smaller number, when it got multiplied by a negative, became a smaller negative, and therefore a larger number. The bigger number, when multiplied by a negative, became a bigger negative, and therefore a smaller number. Okay? A bigger negative represents a smaller number because it's further to the left in the number line. So when you multiply or divide an inequality by a negative, you've got to flip the direction of the inequality symbol. So to make this true, when we multiplied here, we had to flip this guy. So instead of a less than, it had to become a greater than, and then it becomes a true statement. Okay? So we want to keep this in mind when we solve something like this. So we have negative 9x is greater than or equal to 18. So negative 9x is greater than or equal to 18. Okay, so I know that x needs to be isolated by dividing both sides of the inequality by negative 9. What I've got to do is flip the direction of the inequality symbol. Right now I have a greater than or equal to. I want a less than or equal to. So negative 9 over negative 9 is 1. You just have x. So x is less than or equal to. 18 over negative 9 is negative 2. Okay? If you forget to flip the direction of the inequality symbol, you will absolutely get the wrong answer. Okay? So you've got to make sure if you're multiplying or dividing both sides of the inequality by a negative value, you flip the direction of the inequality symbol. Very important. So graphically, if x is less than or equal to negative 2 is the boundary. So I'm going to put a bracket at negative 2, and I'm going to shade everything to the left. In interval notation, I'd put negative infinity, comma negative 2. I'm putting a bracket next to negative 2 because it's included, and a parenthesis next to negative infinity. All right, let's take a look at another. So we have negative 1/3 x is less than 2. Again, negative 1/3 x is less than 2. How can I isolate x? Well, I need to multiply both sides by the reciprocal of negative 1/3. Basically, I need to multiply both sides of the inequality by negative 3. So times negative 3 and times negative 3. Now, I am multiplying both sides by a negative, so I've got to flip the direction of the inequality symbol. Right now it's a less than, it's going to become a greater than. I know this is going to cancel, and I'll just have x. And over here, 2 times negative 3 is negative 6. So we get that x is greater than negative 6. In interval notation, I would put a negative 6 next to a parenthesis, again, because it's not included. Then comma, you have the infinity symbol, because this continues forever in the right direction, and then a parenthesis next to that. So graphically, at negative 6, we'd put a parenthesis, and then we would just shade everything going to the right. Okay, again, including this arrow, because the solution region continues forever in the right direction. All right, so now let's talk about how to solve any linear inequality in one variable. You're going to follow, again, the same steps you used for an equation, with just a minor difference, the fact that if you multiply or divide by a negative, you need to flip the direction of the inequality symbol. So the first thing is to simplify each side separately. So combine like terms, clear any parentheses, do all the simplification you need to do. The next thing is to isolate the variable terms on one side and the constants on the other. So again, you can use the addition property of inequality to do that. Then you want to isolate the variable. So you're going to use your multiplication property of inequality to do that. And then lastly, you're going to check. But as I'm going to show you, when you check an inequality, it's much more tedious. Okay, there's a lot more involved than when you checked an equation. So for this one, you kind of put an asterisk next to it and say, if time permits. All right, let's take a look at an example. So we have 2x plus 9 times the quantity x minus 5 is less than 4 times the quantity 4x minus 15. So we have 2x plus 9 times the quantity x minus 5 is less than 4 times the quantity 4x minus 15. So what I want to do here is first simplify each side. So let's go ahead and do that. So over here I have my 2x, and then plus 9 times x is 9x, and then 9 times negative 5 is negative 45. This is less than 4 times 4x is 16x, and then 4 times negative 15 is minus 60. All right, 2x plus 9x is 11x, and then minus 45, and this is less than 16x minus 60. So now I've simplified each side as much as I can, and it's time to move all the variable terms to one side, all the numbers to the other. So I'm going to subtract 16x away from each side of the inequality. So that's going to cancel. I'm going to add 45 to each side of the inequality. That's going to cancel. 11x minus 16x is negative 5x, and this is less than negative 60 plus 45 is negative 15. Okay, so what I want to do now is divide both sides of the inequality by negative 5. But again, because I'm dividing by a negative, I've got to flip the direction of the inequality symbol. Right now it's a less than, it's going to become a greater than. So this becomes x is greater than negative 15 over negative 5 is going to be positive 3. So x is greater than 3. So let me erase all this. And so x is greater than 3. Okay, so in interval notation, we know this would be a parenthesis, a 3, and then an infinity here, and a parenthesis. Graphically, I would put a parenthesis at 3, and then again, I would shade everything to the right. Now, I want to teach you how to check this guy, okay? I'm not going to check anything after this one because it's just so tedious. But essentially what you want to do is replace your inequality symbol in both the original inequality and your solution with an equals. So I would erase this and put equals, and I would check x equals 3. This is my boundary. Again, we talked about the concept of a boundary. It comes up all the time when you work with inequalities. It separates the solution region from the non-solution region. So you can see at 3 here, if I just circle it, everything to the right of 3 is in the solution region and satisfies the inequality. Everything to the left of 3 is in the non-solution region. 3 is included for a non-strict inequality, but not included for a strict inequality. So in other words, if I change this to a less than or equal to, this would become a greater than or equal to, and this guy would be included. I'd have a bracket there. But because we had a strict inequality there, it's not included, and so it's part of the non-solution region, okay? But it's still considered the boundary because it separates the two. We check our boundary. So essentially, I plug a 3 in for each occurrence of x. So I'd plug a 3 in here, and I'd plug a 3 in here, and I'd plug a 3 in here. And I'm looking to see if I get a true statement. So 2 times 3 is 6, plus 3 minus 5 is negative 2. 9 times negative 2 is going to be negative 18. So I can put 6 minus 18. This should be equal to, 4 times 3 is 12. 12 minus 15 is negative 3. You would have 4 times negative 3. So 4 times negative 3 is negative 12. 6 minus 18 is negative 12. So you're good to go here. Okay, so the boundary is good. So now what I want to do is I want to grab a number that's in the solution region, and I want to check that. So this is a less than. So if I check something in the solution region, it should result in a true statement. So let's just grab 5. So we'll plug a 5 in here, and here, and here. So 2 times 5 is 10, plus 5 minus 5 is 0. 0 times 9 is 0. So you just have 10 over here. So this is less than. 4 times 5 is 20. 20 minus 15 is 5. And then 5 times 4 is 20. So is 10 less than 20? Yes, this is true. So you're good to go there. Then you want to check something on the other side of the boundary, so something in the non-solution region. Let's just choose 0 because it's easy to work with. So we'll plug a 0 in there, and also here. Okay. All right, so 2 times 0 is 0, so that's gone. 0 minus 5 is negative 5. 9 times negative 5 is negative 45. So this is less than. 4 times 0 is 0. 0 minus 15 is negative 15. 4 times negative 15 is negative 60. So is negative 45 less than negative 60? No, it isn't. Right? Negative 45 is a smaller negative and therefore a larger number. So this is false. Okay? And that's good because we picked a number in the non-solution region. It should not work. So we verified that our solution here, which is x is greater than 3, is correct. All right, let's take a look at another one. So we have negative 5 times the quantity 5x minus 11 minus 9 is greater than or equal to 7 times the quantity 9x minus 6. So again, I'm going to start by simplifying each side. So negative 5 times 5x is negative 25x. Then negative 5 times negative 11 is plus 55. Then minus 9, and this is greater than or equal to 7 times 9x is 63x. And then minus 7 times 6 is 42. So on the left side, 55 minus 9 is 46. So I can say this is negative 25x plus 46. This is greater than or equal to, we have 63x minus 42. Scroll down, get some room going. Now I just want to get all the variable terms to one side, all the numbers to the other. So let's subtract 46 away from each side. And let's go ahead and subtract 63x from each side. So this is going to cancel, and this is going to cancel. Negative 25x minus 63x is negative 88x. This is greater than or equal to negative 42 minus 46 is negative 88. Okay. So to get x by itself, we divide both sides of the inequality by negative 88. And this guy's going to flip because I divided by a negative. So you get x is less than or equal to 1. Okay, x is less than or equal to 1. So let's erase all this. So x is less than or equal to 1. If x is less than or equal to 1, then at 1, I'd put a bracket, and then I would shade everything to the left. And then in interval notation, I would have a negative infinity, and then comma, I would have a 1, and then just make sure you put a bracket there because 1 is included. Let's take a look at another one. So we have negative 3 times the quantity 3x plus 1, and then is greater than negative 2x plus 3 times the quantity x minus 2. So again, I'm going to simplify each side to start. Negative 3 times 3x is negative 9x. And then negative 3 times 1 is minus 3. This is greater than, you have negative 2x. And then plus, you have 3 times x, which is 3x. And then minus 3 times 2 is 6. So on the right side here, negative 2x plus 3x is just x. So we'll just put x minus 6 like that. Now I'm going to get all the variable terms to one side and all the numbers to the other. So I'm going to subtract x away from each side of the inequality. I'm going to add 3 to each side of the inequality. And this guy's going to cancel, and this guy's going to cancel. So negative 9x minus x is negative 10x. And this is greater than, negative 6 plus 3 is going to be negative 3. So to finish this up, let me kind of erase this. To finish this up, I'm just going to divide both sides of the inequality by negative 10. And again, I've got to flip the direction of the inequality symbol. So negative 10 over negative 10 is obviously 1. So you have x is less than. You have negative 3 over negative 10, which is just 3/10. So in interval notation, I'll have my negative infinity, and then I'll have 3/10. And then again, I've got to use a parenthesis next to 3/10 because it's not included. So graphically, we have this in a scale that represents the integers. 3 divided by 10 is 0.3. So let's just say it's about right here. I'm just going to write a little marking there and say this is 3/10. And in other words, I would just go ahead and put a parenthesis there and just shade everything to the left. Okay. If you're working with a pre-drawn graph like that, just find out an area that makes sense, put a little marking and notate it. In this case, we're just notating it to say we have 3/10, and we just draw a little arrow going there to say, hey, this is 3/10. Put your parenthesis in this case because it's not included, and then just shade everything to the left. All right, for the last one, we'll look at one with some fractions involved. So we have 4/3 times the quantity x plus 5/2 is greater than or equal to, you have -2 times the quantity negative 4x over 3 plus 5/3. So if you want to clear the fractions, let's go ahead and clear the parentheses first. So 4/3 times x is just 4/3 x. Then plus 4/3 times 5/2 would be 20 over 6. This is greater than or equal to -2 times negative 4/3 x would be positive 8/3 x. Then -2 times 5/3 would be minus 10/3. Okay? So to clear the fractions, I'd multiply both sides of the inequality by the LCD. Okay? And what's that going to be? We have a 3, a 6, a 3, and a 3. So I'll put a 6 here and here. And let me kind of scooch this down. So 6 times 4/3 x. Think about 6 divided by 3 is 2. 2 times 4 is 8. So this would be 8x. Then plus 6 times 20 over 6. The 6's would cancel. You just have 20. Then you would have a greater than or equal to 6 times 8/3 x. 6 would cancel with 3 and give me 2. 2 times 8 is 16. So this is 16x. And then minus 6 times 10/3. 6 would cancel with 3 and give me 2. 2 times 10 is 20. So let's move all the numbers to one side and all the variable terms to the other. So I'm going to subtract 20 away from each side of the inequality. And I'm going to subtract 16x away from each side of the inequality. So this is going to cancel, and this is going to cancel. 8x minus 16x is going to give me negative 8x. This is greater than or equal to negative 20 minus 20 is negative 40. So very easy at this point. We divide both sides of the inequality by negative 8. And again, we're dividing by a negative, so we've got to flip the direction of the inequality symbol. This will be a less than or equal to now. So you get x is less than or equal to negative 40 over negative 8 is 5. So let's erase everything. So again, x is less than or equal to 5. So in interval notation, we know that would be, we have a negative infinity here on the left, and then we have a 5 on the right with a bracket next to it, okay, because 5 is included. Find 5 on the number line, and we're going to put a bracket there. And we're going to shade everything to the left, our solution region. In this lesson, we want to review solving a 3-part inequality. So in the last lesson, we reviewed how to solve any linear inequality in one variable. In this lesson, we just want to talk a little bit about 3-part inequalities and kind of set the stage for our next lesson where we're really going to start talking about compound inequalities. So if we have something like negative 11 is less than x minus 5, which is less than 4, how could we solve this for x? Well, let's rewrite this first. We have x minus 5 that's in the middle. We can say that this is greater than negative 11. And we can use a special keyword here. We could say, and it's less than 4. So we don't have to write it like this. We can kind of split this guy up using that keyword and I'll show you how to do that in a minute. The first way I want to show you how to solve this is to basically do the same thing to each part. So you have a part right here on the left, you have a part right here in the middle, and you have a part right here on the right. So that's why we say a 3-part inequality. My goal is to isolate the variable x in the middle. I want x to be between two numbers. And so what I want to do is add 5 to each part because I'm subtracting 5 away here in the middle. So if I add 5 in the middle, and then I add 5 on the right, and then I add 5 on the left, what's going to happen is this negative 5 and this plus 5 here, those are going to cancel, right? Negative 5 plus 5 is 0. So we get x in the middle, and we could say this is greater than negative 11 plus 5 is going to give me negative 6. And we could say, and it's less than 4 plus 5 is 9. So realize what this is saying. This is saying that x is between -6 and 9. In other words, x has to be greater than -6 and also less than 9. So let's kind of look at this on the number line so we can fully understand this concept. Let's kind of drag this up here, and let's take a look at this guy. So if I wanted a number that was between -6 and 9, and it's not inclusive because these are strict inequalities, I would find -6 on my number line, which is right here. I would put a parenthesis facing to the right. Then I would find 9, which is right here. I would put a parenthesis facing to the left. And then I would shade everything in between. So the area that I shaded there, that represents all the solutions that are possible for x. If I grab any number in that range, any number that's in the shaded area, it will work. Let's grab one. Let's say we chose 3 as an example. So we would have -6 is less than 3, which is less than 9. Is that a true statement? Is 3 greater than -6? Yes. Is 3 less than 9? Yes. So this is true. Both parts have to be true. If I grab something outside of the shaded area, let's say I grabbed -7 as an example, what's going to happen is it'll be true in one scenario but false in the other, and so it's false for the 3-part inequality. So let's say we did -6 is less than -7, which is less than 9. Okay, is that true? Is -7 greater than -6? Nope, that's false, right? That's false. So you can mark the whole thing as false, even though you could say that -7 is less than 9. That part's true. But the whole thing's got to be true. It's got to be larger than -6 and also less than 9. So the numbers that fit that criteria are in this shaded area here, okay? Where -6 and 9 are kind of the endpoints. They're not included. Those are the boundaries. And everything in between works as a solution. Now, the other way you can think about this is you can split this guy up using the keyword and that I mentioned, okay? So you could take this guy x minus 5, and you could say this is greater than -11. Okay, so you solve that as one problem. You use your keyword and. Then you're going to take the other side, so you're going to say x minus 5, and you're going to set that as less than 4. So you solve these individually, and then you put them back together with that keyword and. So what I would do is just add 5 to each side of the inequality here. So -11 plus 5 is -6. This is less than. This cancels. You just have x. So then again, you have the keyword and. Here you add 5 to each side of the inequality. So you get x is less than 9. So we have that x is greater than -6 and x is less than 9. So in other words, both of these have to be true. It's the same thing. It's just a little bit easier to understand when you put x in the middle and you say x is greater than -6 and less than 9, right? Because this way it's crystal clear that x is a number between -6 and 9, with -6 and 9 not being included because, again, these are strict inequalities. If you want to, besides graphing this guy, you can, of course, write it in interval notation. And so I can say that my solution here, I'd put a -6 next to a parenthesis because the -6 is not included, comma, I'd put a 9, and again, a parenthesis next to 9 because it's not included. So this is kind of two different ways to notate this, and then you have a way to graph it, right? So that's kind of the solution for this 3-part inequality. In the next section, we're going to talk more about compound inequalities with and you're going to see that in some scenarios, you can't start out writing them as a 3-part inequality. They're going to have to be broken up, okay? Because you're going to have more than just a variable expression in the middle. You're going to have variable expressions all over the place, and so it's not going to allow you to basically write it in this format. This is the easier scenario. So let's go ahead and take a look at another one. All right, for the next one, we have -63 is less than or equal to 10x plus 7, which is less than or equal to 77. Or you could use your and keyword. You could say 10x plus 7 is greater than or equal to -63, and it's less than or equal to 77. Okay, so you could break it up if you wanted to. In this specific situation, because you just have this variable expression in the middle, it's just easier to work it by kind of doing the same thing to each part. If you split it up, you got to put it back together, so it's just extra work. So we have -63 is less than or equal to, again, 10x plus 7, which is less than or equal to 77. Okay, so let's solve this guy. Very, very easy. I want to isolate x in the middle. So since 7 is being added to this term 10x, I want to subtract 7 away from each part. Okay, so from each part. So that's going to cancel. So in the middle, I'll just have 10x. And then on the left-hand side, negative 63 minus 7 is negative 70. On my right-hand side, 77 minus 7 is going to be positive 70. Now, I want to isolate x right here. Since I'm multiplying x by 10, what I'm going to do is I'm going to divide each part by 10, right? So I can isolate x. So in the middle, we'll have x. And so it's going to be greater than or equal to negative 70 divided by 10 is negative 7. And it's less than or equal to 70 divided by 10 is 7. So we see that x is greater than or equal to negative 7, and it's less than or equal to 7. Okay? So let's erase all this. I'll kind of drag this up to the number line. So in interval notation, you have non-strict inequalities here. So you're going to put a bracket next to negative 7, then comma, you'll have a positive 7 and another bracket. Graphically, I'm going to find negative 7. I'm going to put a bracket. I'm going to find positive 7. I'm going to put a bracket. And I'm just going to shade everything in between there. So the solution here for x is any value that's between negative 7 and 7 with negative 7 and 7 included, right? Because we have, again, non-strict inequalities. All right, for the next one, let's take a look at an example with some fractions involved. So we have negative 16 fifths is less than or equal to negative 7 halves x plus 19 fifths, which is less than, you have 159 fifths. So the first thing I'm going to do is clear the fractions. Again, if you want to work with the fractions, it doesn't really matter. For me, I like to not work with fractions because it just makes the inequality a lot cleaner. So the LCD here, you have 5, you have 2, you have 5, and you have 5. It's basically 5 times 2 or 10. So if I multiplied each guy here by 10, what would I have? Well, 10 multiplied by this guy right here, the 5 and the 10 would cancel and give me a 2. 2 times negative 16 is negative 32. So you'd have negative 32 is less than or equal to. If I multiplied this guy by 10, 10 divided by 2 is 5. 5 times negative 7 is negative 35. And then times x. Then over here, if I multiply this by 10, 10 would cancel with 5 and give me 2. 2 times 19 is 38. So plus 38. And then this is less than. If I multiply this guy by 10, 10 divided by 5 is again 2. 2 times 159 is 318. Okay, 318. All right, so from this point, it's pretty easy. I just want to isolate x in the middle. So all I need to do is start out by just subtracting 38 away from each part. And negative 32 minus 38 is going to be negative 70. And this is less than or equal to, you have negative 35x. This canceled. And this is less than 318 minus 38 is going to be 280. So now all I want to do is isolate x in the middle. So I'm going to divide each part by negative 35. But I've got to be very careful here because, again, when I work with inequalities, if I multiply or divide by a negative, I've got to flip the direction of the inequality symbol. So that means that this guy right here has to get flipped, and this guy has to get flipped. So this one is a less than or equal to, it will become a greater than or equal to. This is a less than, it will become a greater than. So x will be in the middle. Negative 70 over negative 35 is going to be positive 2. And 280 over negative 35 is negative 8. Okay. Now, although this is technically correct because your symbols are each pointing towards the smaller number of negative 8, you generally want to order this the same way you would see things on a number line. Negative 8 is less than x, which is less than or equal to 2. Okay. Typically, you're just working with less than or equal to symbols when you work with a three-part inequality, because this is not technically in the order of the number line, although it is valid because the signs are both pointing to the smaller number. Okay, but this is generally what we do. Now let me erase everything. All right, so to put this in interval notation, negative 8 is not included. So I'm going to put a parenthesis and then a negative 8. And then 2 is included, so I'm going to put a 2 and then a bracket. Now graphically, I'm going to follow the same format. I'm going to put a parenthesis at negative 8. And I'm going to put a bracket at 2. And I'm just going to shade everything in between. Okay, everything in between. So x is greater than negative 8, and also it's less than or equal to 2. So any number in the shaded region, including 2, because again, we use a non-strict inequality here, but not including negative 8 because we used a strict inequality there. All right, let's take a look at one more. So we have negative 1 is less than or equal to 2x minus 5 over 6, which is less than or equal to 2. All right, so the idea here is to start out by just multiplying each part by 6 so I can get rid of that denominator. So let's just copy our problem here. We have negative 1 is less than or equal to 2x minus 5. Again, this is over 6, which is less than or equal to 2. All right, so if I want to clear that denominator of 6, I can multiply each part by 6. And what's going to happen is this guy over here is going to cancel, right? 6 over 6 is 1, so that's gone. On the left, 6 times negative 1 is negative 6. So this is less than or equal to. You'll have your 2x minus 5, and this is less than or equal to. 2 times 6 is just 12. So let's get some room going. All I want to do now is just add 5 to each part. Very, very simple, so that this part goes away. Negative 6 plus 5 is negative 1. So this is less than or equal to. Now you just have 2x in the middle, and this is less than or equal to. 12 plus 5 is 17. Okay? So the last thing here is to isolate x. And to do that, I'm multiplying x by 2. So I just divide each part by 2. So what I'm going to end up with is that x is going to be greater than or equal to negative 1/2. And it's less than or equal to 17/2. Okay? So let's erase everything. So in interval notation, I'm going to basically use a bracket with each of these numbers. I'd have a bracket and then a negative 1/2, then comma, I'd have a 17/2, and then a bracket. Now when we go to do our graphical solution here, our number line is arranged in a scale with integers involved. That's okay. We know that negative 1/2 would be pretty much about right here. So I'm just going to put a marking there in between 0 and negative 1, basically where I see the halfway mark. And I'll just put a little arrow there saying this is negative 1/2. And I'm going to put a bracket there, okay, facing to the right. All right, so 17/2, that's basically going to be 8.5. So I'm going to go halfway between 8 and 9. I'm going to put a little mark there, draw my arrow, and say this is 17/2. Again, I'm just going to put a bracket there. And now I can shade everything in between. So we can say that x is greater than or equal to negative 1/2. And it's also less than or equal to 17/2. So x can be any value between negative 1/2 and 17/2 with negative 1/2 and 17/2 included. In this lesson, we want to review solving compound linear inequalities with and, or. So in our last lesson, we talked about how to solve a 3-part inequality. And essentially, we looked at problems like, let's say negative 4 is less than, you have something like 3x plus 5, which is less than 20, okay? Now, we can leave it like this, or we learned that we could split this up using the special keyword and, okay? So we could also write the same problem as negative 4 is less than 3x plus 5. And then we would say and you would have 3x plus 5 is less than 20. Now, you wouldn't go through the trouble of splitting this up because this is kind of more complex or more tedious, not more complex, more tedious to solve it in this manner. To solve a 3-part inequality, all you need to do is do the same thing to each part. Your goal is to isolate x in the middle, okay? Notice how you just have a variable expression, the 3x plus 5 in the middle. You don't have a variable on the left and you don't have a variable on the right, okay? So all I need to do is just subtract 5 away from each part. Let me kind of slide this down for a moment. And let me slide this up. So negative 4 minus 5 is going to be negative 9. So this is less than 3x. And this is less than 20 minus 5 is 15. Okay. So now to isolate x, I just need to divide each part by 3. Very, very simple. And what I'm going to have is, let me kind of erase this. We don't need it. 3 divided by 3 is 1. So you just have x in the middle. This is greater than, negative 9 divided by 3 is negative 3. And it's going to be less than 15 divided by 3 is 5. So essentially what we're saying here is that x is a number that is between negative 3 and 5 with negative 3 and 5 not included. Okay, so it's very easy to look at it in this format here and understand the context of what we're talking about. If I looked at a number line, again, if x is greater than negative 3 and less than 5, well, I know that graphically I could just put a parenthesis at negative 3 and a parenthesis at 5, and I could shade everything in between, right? Those numbers that I shaded there represent solutions for x. If I take any number that's shaded and I plug it in there, I'm going to get a true statement, right? So if I plug in a 2, we could say that 2 is greater than -3, and it's also less than 5, right? Both have to be true. That's the key when you're working with something with and, okay? Both have to be true. If I plugged in something outside of what I shaded, let's say I just took 6, both are not going to be true here. 6 is greater than -3. That part's true. But 6 is not less than 5. 6 is a larger number. So that part's false, so the whole thing's false, okay? So when you work with an inequality and you have and involved, you've got to think about satisfying both requirements. You can think about it as looking at a job listing that says, okay, you've got to be 21 and have a valid driver's license. Okay, you've got to have both, otherwise no job for you, right? If you're 18 and have a valid driver's license, that sucks, you don't qualify. If you're 22 but you don't have a valid driver's license, that sucks, you don't qualify. I want to jump into some more complex problems with and. These are problems that we typically cannot write as a 3-part inequality. So you see that you have more variables involved. With a 3-part inequality, you can break that up and use and, but you just have one variable expression in the middle. You have a number on the left side and a number on the right side. With these guys, you have 7 minus 17x is less than -13x minus 5. And then you have and, you have -11x minus 14 is less than or equal to -12x minus 5. So you can't write that as a 3-part inequality. So you're going to have to go through the method of solving each one individually and then looking at the intersection of the solution sets. In other words, the areas that satisfy both inequalities. Okay, that's what you're looking for. All right, so let's start with the first one. We have 7 minus 17x is less than -13x minus 5. All right, let's get some room going. We'll come back up. So all I want to do is just subtract 7 away from each side of the inequality. And so I know that this is going to cancel. And -5 minus 7 is -12. I want to add 13x to both sides of the inequality. That's going to cancel. And let me put my less than symbol there. -17x plus 13x is going to give me -4x. So to solve this, I just want to divide each side by -4. And remember, if I work with an inequality, what do I have to do if I divide by a negative? I've got to flip the direction of the inequality symbol. So this cancels with this. I've got x is now greater than, okay, my less than became a greater than, -12 over -4 is 3. So let's erase this and go back up. So the solution for this part is that x is greater than 3. Okay. Now let's solve this part. What I want to do is I want to add 14 to each side of my inequality. That will cancel. I want to add 12x to each side of my inequality. That will cancel. -11x plus 12x is x. So x is less than or equal to -5 plus 14 is going to give me 9. So we have this x is less than or equal to 9. So let's think about this using my keyword and. Essentially what I have is that x is greater than 3 and x is less than or equal to 9. So again, it goes back to my job listing scenario. You've got to be 21 and you've got to have a driver's license. Well, here x has to be greater than 3 and it's also got to be less than or equal to 9. Let's copy this real quick, and I want to show you this on a number line real quick. So I've got 2 of these guys, and I'm just going to basically do one on the top and one on the bottom, and we'll see the intersection or the overlap between the 2 graphs. So if x is greater than 3, I'd put a parenthesis at 3, just shade everything to the right. Then for x is less than or equal to 9, I'm going to put a bracket at 9, and I'm going to shade everything to the left. All right, so essentially what I'm doing is I'm looking for the overlap. So you see this guy right here, if we kind of just put a little dash going down here, 3 is not going to be included, right? So essentially I'm just going to copy this marking and put that here. And everything to the left of 3 is not included because in this solution, it's only things that are larger than 3. So it's got to work for both, and since nothing to the left of 3 and including 3 doesn't work in this one, it can't work in this one. So let me erase this shading. Here, it's anything that's less than 9, so it can go all the way down to the point of 3, but it can't be 3 itself. So let's just shade from here to here, okay? So this is the overlap of the two solutions, okay? So that's what we're looking at. And essentially I can write this with x in the middle. I can say that x is going to be larger or greater than 3 and less than or equal to 9. And it's also very convenient to write this in interval notation. I can go ahead and say I have a 3, and I have a parenthesis next to that because it's not included. And then comma, I'm going to have my 9, and then a bracket next to 9 because 9 is included. But again, it's got to satisfy both. So again, if I took a number like 6 and I plugged it in there, 6 is greater than 3, and it's also less than or equal to 9. So that's good. If I took something outside of that, if I took 0, 0 is not greater than 3. That doesn't work. 0 is less than or equal to 9, but it doesn't satisfy the first one. And if it doesn't satisfy both, it doesn't work. Again, just think about the example with the have to be 21 and have to have a valid driver's license. You got to have both or you're not getting a job. Okay, so that's the idea. All right, let's take a look at another one with and. So we have 11x minus 2 is less than 18 minus 9x. And we have 16x plus 7 is greater than 1 plus 15x. All right. So all I want to do is just solve these individually and then again just put the solutions together. So I have 11x minus 2 is less than 18 minus 9x. You scroll down and get a little bit of room going. We'll come back up. So I'm going to add 2 to each side of the inequality. So that's going to cancel. 18 plus 2 is 20. I'm going to add 9x to each side of the inequality. And this is going to cancel. So I'll have the less than symbol there. 11x plus 9x is 20x. To get x by itself, very easy. I just divide both sides of the inequality by 20. And I get that x is less than 1. Okay, 20 over 20 is obviously 1. So let's erase everything. So we'll say here that x is less than 1. All right, let's solve this guy now. So if I have 16x plus 7 is greater than 1 plus 15x, again, I'm just going to go ahead and subtract 7 away from each side of the inequality. That cancels. I'm going to subtract 15x away from each side of the inequality. And this is going to cancel. So on the left, 16x minus 15x is going to be x. This is going to be greater than 1 minus 7 is negative 6. So we have x is greater than negative 6. And again, we have this keyword and. So we're looking for the intersection of those two solution sets. So x needs to be less than 1 and x needs to be greater than negative 6. So you can think about this again by putting x in the middle and saying it's greater than negative 6 and less than 1. Okay, so it's between negative 6 and 1, not including either. So let's take this to the number line. All right, so in interval notation, essentially all I would need to do is put a parenthesis, a negative 6, a 1, and a parenthesis, right? Because negative 6 and 1 are not included, so you've got a parenthesis next to each one. I'm just basically going to match this format on my number line. X is between negative 6 and 1, and negative 6 and 1 are not included. So a parenthesis at negative 6, a parenthesis at 1. I'm just going to shade everything in between. All right, let's take a look at one more of these with and then we're going to move on to the keyword or. So we have 5x plus 15 is less than or equal to 8x minus 12. And then we have 15x minus 3 is less than 14x minus 4. So we'll start out with the guy on the top. We have 5x plus 15 is less than or equal to, we have 8x minus 12. So I'm going to subtract 15 away from each side here. So that's going to cancel. You're going to have 5x is less than or equal to, you'll have 8x, and then negative 12 minus 15 is negative 27. I'm going to subtract 8x away from each side of the inequality. So that'll cancel. And I'll have 5x minus 8x, which is negative 3x. And basically, this is less than or equal to negative 27. So if I divide each side here by negative 3, again, what do I got to do? I've got to flip the direction of the inequality symbol. So this becomes a greater than or equal to. So I would have x is greater than or equal to. Negative 27 divided by negative 3 is positive 9. So we've got x is greater than or equal to 9. So we have x is greater than or equal to 9. Okay, for this guy right here, I would add 3 to each side of the inequality, and then I would subtract 14x from each side of the inequality. So that's going to cancel, and that's going to cancel. 15x minus 14x is x, and this is less than. Negative 4 plus 3 is negative 1. So let's erase this. We're going to say that x is less than -1 here. So again, when we put our kind of and statement in between these two, we get that x is greater than or equal to 9 and x is less than -1. Okay, x is less than -1. Now, before we kind of think about this, let's look at a number line real quick and see where we get a problem here. So let's paste this guy right here. Let's first graph x is greater than or equal to 9. So at 9, I would put a bracket and I would shade everything to the right. Let's graph x is less than -1. So at -1, I would put a parenthesis facing to the left and I would shade everything to the left here. Okay, all of this area. Now, do you see an overlap between the two solution sets? No, you don't. You can't have a number that is less than -1 and greater than or equal to 9. It's not possible, okay? So when this happens and you're using the keyword and, you don't have a solution. So for the compound inequality, you just say no solution, right? Individually, for each inequality, there's a solution. But for the compound inequality, again, for the overlap of the two solution sets, it's not possible. So you just put no solution. A lot of teachers will like you to put the symbol for the null or empty set. It's that right there. So you can put that as well. But you're basically just saying that there's no solution. All right, so now let's think about the keyword or when we're talking about compound inequality. So let's go back to our example with the job. With and, we said we had to be 21 and have a valid driver's license. Okay, you had to have both. But let's say we replaced it and said you had to be 21 or have a valid driver's license. What does that mean? It means if I have a valid driver's license, it doesn't matter how old I am. I can apply for the job and I can get it. It also means if I don't have a driver's license and I'm 21, I can apply for the job and I can get it. If I don't have either, right, if I'm not 21 and I don't have a driver's license, well, then I don't get a job, right? But if I have at least one of them, then I'm okay. If I have both, I'm okay. So that's the situation with or, right? It can be either of them or it can be both of them, okay? So if we look at 9x plus 20 is less than 16 plus 11x, or negative x plus 13 is greater than 5x plus 19. Okay, so we're going to solve each one individually again. So let's write this one down here. We have 9x plus 20 is less than 16 plus 11x. Let me get a little room going. Come back up. So what we want to do is subtract 20 away from each side. And let's just go ahead and subtract 11x away from each side. And we can cancel this and we can cancel this. And what do we have here? 9x minus 11x is negative 2x. This is less than 16 minus 20 is negative 4. So to get x by itself, I just divide both sides by negative 2. And I've got to flip the direction of the inequality symbol because I divided by a negative. Right now it's a less than. It's going to become a greater than. We would have x is greater than. Negative 4 over negative 2 is 2. So we've got x is greater than 2. So let's erase all this. So x is greater than 2. Okay. For this one right here, we can subtract 5x away from each side. And we can subtract 13 away from each side. So this cancels and this cancels. You would have negative x minus 5x, that's negative 6x. This is greater than. 19 minus 13 is going to be 6. We would divide each side by negative 6. And again, I'm dividing by a negative, so I've got to flip the direction of the inequality symbol. It's a greater than right now, so it's going to become a less than. So x is less than. 6 over negative 6 is negative 1. So we would have or x is less than negative 1. So let's erase this. And again, all I'm going to do here, I'm just going to drag this down to the number line. So if x is greater than 2, I can put a parenthesis at 2, and I can just shade everything to the right. For x to be less than negative 1, I could put a parenthesis at negative 1, and I could shade everything to the left. Okay. Think about the fact that if you had and here, you would not have a solution. There's no overlap. But we don't have and. We have or. Remember, if I'm going for my job and there's an or, I can be 21 or have a valid driver's license. I can get it either way. So here, x can be greater than 2, or it could also be less than negative 1. Either of these works, okay? Either of these works. The only numbers that don't work are from negative 1 to 2 with negative 1 and 2 included, okay? So in interval notation, to kind of show this concept, we need to use a union symbol. Some of you have seen this. You've talked about sets before. We'll talk about sets more in depth later on in the course. But for right now, you have this U looking symbol, and it stands for the union, okay? It's not an actual U, but it looks like a U. So this is the union. So I'm going to place this between the two intervals to combine them as a union, okay? So what I'm going to do is I'm going to say that x can be from negative infinity up to and not including negative 1. So that's kind of the first solution here. That's this one right here. That's the one coming from the left, coming from negative infinity up to but not including negative 1. So I'm always going to put that on the left because it's on the left in the number line, right? And then I want to use my union symbol. So I want to use my union symbol. Again, looks like a U. It's not a U, but it looks like one. And then I'm going to look at the solution on the right in terms of the number line. So it's going to start with any number greater than 2. So I'm going to put a 2 next to a parenthesis, and then comma, it goes out to positive infinity, okay? So it's again, the union of the two solution sets. You've got this guy right here, again, coming from negative infinity up to but not including negative 1. It's the union with this guy right here, anything larger than 2, again, going out to positive infinity. All right, let's take a look at one more of these. Very, very easy concept overall. So we have 15 plus 13x is greater than or equal to, you have 5 plus 18x, then or, you have 1 plus 5x is greater than 4x minus 6. Again, I'm just going to write this one down here. So 15 plus 13x is greater than or equal to, you have 5 plus 18x. So what I want to do, I want to subtract 15 away from each side. So that's going to cancel. And I want to go ahead and subtract 18x away from each side. Let me make that 8 a little bit better. So that's going to cancel. All right, let me get a little room going here. So 13x minus 18x is going to be negative 5x. This is greater than or equal to 5 minus 15, or 5 plus negative 15 is negative 10. And so I'm going to divide each side by negative 5 so that I can isolate my variable x. Negative 5 over negative 5 is obviously 1. You would have x is, remember we divided by a negative, so this gets flipped. X is less than or equal to 2, right? Negative 10 over negative 5 is positive 2. So x is less than or equal to 2. So again, x is less than or equal to 2. Okay, for this guy right here, I'm going to subtract 1 away from each side. That cancels. I'm going to subtract 4x away from each side. That cancels. 5x minus 4x is x. This is greater than. Negative 6 minus 1 is negative 7. So you just get that x is greater than negative 7. All right, so let's think about this again using our number line. A lot of times it's very easy to visualize the solution. So we have x is less than or equal to 2, or we have x is greater than negative 7. So let's go ahead and copy this. All right, so let's think about x is greater than negative 7. So greater than negative 7, I'm just going to put a parenthesis at negative 7, and I'm going to shade everything going to the right, including my arrow. And for x is less than or equal to 2, I would go to 2 and I would put a bracket there. And I would go ahead and shade everything going to the left. Let me use a different color here. So I would shade everything going to the left. So what you'll see here is that your solution set would be all real numbers. So any real number would work in at least one of them. So the ones that would work in both fall in the category of between negative 7 and 2, with negative 7 not being included because it's a strict inequality, and 2 being included because it's a non-strict inequality. So any number in that range would satisfy both, okay? But outside of that range, we would fall in the category of one of them. So it would work in one and not work in the other. But again, because we have the or, it only has to work in one of them. So I can take any real number that I would like, and I would get a correct answer if I plugged it into the compound inequality, again, because of the or. Okay, so I can just say that my solution here is all real numbers. Okay. Now, one way you can notate this, we can just erase kind of these markings here. You can just shade the entire number line graphically. So I can just shade this whole thing and just say that they all work. Okay, everything from negative infinity to positive infinity. In interval notation, that's exactly what you would put. You would put from negative infinity to positive infinity. So all real numbers. In this lesson, we want to review solving absolute value equations. So before we jump in and start looking at problems where we're solving absolute value equations, we want to make sure that we have a good understanding of the concept of absolute value. So this is something we reviewed at the beginning of the course. So if I said I want the absolute value of the number 7, what am I asking for? Well, the absolute value of a number is the distance from the number to 0 on the number line. So if I want the absolute value of 7, this is equal to 7 because if I started at 7 on the number line and I counted how many units I'd have to go to get to 0, we all know it would be 7, right? Start here, you go 1, 2, 3, 4, 5, 6, and then lastly 7 units to get to 0. Similarly, if I wanted the absolute value of -7, it's also 7 because if I start at -7 and I want to get to 0, I got to go 7 units to the right. So 1, 2, 3, 4, 5, 6, and then finally 7. So these two numbers, 7 and -7, are known as opposites, okay? They have the same absolute value. In each case, it's 7, but they lie on opposite sides of the number line. So one's going to be negative and one's going to be positive, right? So you have something like -2 and +2, or -2/3 and +2/3, or -2 million and +2 million, right? So on and so forth. When we take the concept of absolute value and we start working with variables, you really have to think a little bit. So if I had something like the absolute value of x equals 5, what could I plug in for x there and get a true statement? So the absolute value of x is equal to 5. So in other words, I am asking for a value that when plugged in here, I would take the absolute value of it, meaning I want to find the distance between that number and 0 on the number line, and it should be equal to 5. Well, what numbers have an absolute value of 5? Well, it's only going to be 5 and -5, right? So 5 and -5. Okay, so that's what I can plug in for x. If I plug in a 5 there and I evaluate, I get 5 equals 5. That's true. But again, that's not the only solution because -5, the opposite of 5, also has an absolute value of 5. So if I plugged in a -5 for x, you would get 5 equals 5 as well, which is also a true statement. So what ends up happening is we're going to say that our solution for this equation is going to be what? It's going to be that x could be equal to 5. And then we have that keyword or that we talked about in the last lesson with compound inequalities. So x equals 5 or x equals -5. Again, the or just tells me that either works. If I plug in a 5 here, take the absolute value, I get 5. 5 equals 5, that's true. If I plug in a -5, absolute value of -5 is also 5. 5 equals 5, that's also true. So either one works. That's why we use the or keyword. Now, in most cases, we're not going to get something as simple as the absolute value of x equals some number, okay? We're going to have some absolute value of an expression equal to some number, or later on we'll see things get more complicated than that. But essentially, if you have an equation in this format, you have the absolute value operation isolated on one side with an algebraic expression inside of the absolute value bars, and it's equal to some non-negative number like k, then we can go ahead and set up a compound equation with or. We can say that this guy right here, the ax plus b could be equal to k, or ax plus b could be equal to the negative of k, all right? Now, it's hard to understand this when you look at it in this generic formula, but I want you just to jot this down in your notes anyway. And let's look at the first example, and we're going to kind of relate back to this. So we have the absolute value of x minus 3 is equal to 4. So you see that you have the absolute value operation isolated on one side. You have some non-negative number on the other. Okay, so we're good to go there. So essentially what my formula told me to do was to take this expression here, so x minus 3, and set it equal to this number. So equal to k. Remember, in this case, k is just 4. So equal to 4. Then or, you take your expression again, so x minus 3 could be equal to -4. Okay, remember you said negative k, now it's just -4. Now, why does this thought process work? Well, think about it. If I find a value for x that when I plug it in here and I subtract away 3, it's going to give me 4. Basically, I'm going to be evaluating the absolute value of 4, and that is 4. So I'm good to go there. Alternatively, if I find a value for x, then when I subtract away 3, I get -4. Well, I'm going to be evaluating the absolute value of negative 4, which is also positive 4. So that's what I'm looking for. I'm looking to get a result inside of the absolute value bars here of either 4 or negative 4. Doesn't matter which one it is, because in each case, I will get a value of 4. So let's go ahead and solve this really quickly. On this one, I would just add 3 to each side of the equation. I'm going to get that x is equal to 7. For this one, I'm going to add 3 to each side of the equation, and I'm going to get that x is equal to negative 1. So let's check these. It's very easy to do. So I'm going to plug in a 7 for x here. So I would have the absolute value of 7 minus 3 is equal to 4. So 7 minus 3 is 4. So I would have the absolute value of 4 equals 4. And of course, that's true. 4 does equal 4. So that's a big check. Okay, so that works. Now, let's check the other scenario. We have x equals negative 1. So if I plug in a negative 1 for x right there, so negative 1 minus 3, we're taking the absolute value of that. This should be equal to 4. Negative 1 minus 3 is negative 4. So you'd have the absolute value of negative 4 is equal to 4, and we know that's true, right? The absolute value of negative 4 is 4, so you get, again, 4 equals 4. So this one's a big check too. So you can see how that ends up working, right? You take this expression right here, this guy, and you set it equal to this number, and then the negative of that number. You solve those two equations, you kind of put it together with that keyword or, and then you're going to have your solution. So there's a few different ways to notate the solution. You can kind of remove these check marks. You don't need them anymore. You can just put an or there between them. So x equals 7 or x equals negative 1. That's fine. You can use the solution set notation and say you have negative 1 and 7 as the elements, or basically solutions that work for your equation. And then lastly, you could also do this. You could say x equals 7, comma, negative 1, right? Lots of different ways to notate this, but just make sure that you're indicating that each one is a solution to your equation. All right, let's take a look at another one. So we have the absolute value of 5x minus 4 is equal to 6. So again, we're following the same thought process. We're going to take this expression inside the absolute value bars. So 5x minus 4, we're going to set it equal to 6. Then we're going to have or, we're going to have 5x minus 4 is equal to the negative of 6. Okay. So what I want to do, I want to solve each one of these. So I want to add 4 to each side of the equation here. That's going to cancel. I'll have 5x is equal to 10. Divide both sides by 5. And I'll get that x is equal to 2. Over here, I just want to add 4 to each side. That's going to cancel. I'll have 5x is equal to, you'll have negative 2. Divide both sides by 5. And you'll have that x is equal to negative 2/5. All right, so let's erase these. So I'm going to go ahead and say that x is equal to 2 or x is equal to negative 2/5, like that. Again, you can write it that way. You can use the solution set notation. A lot of books do that. Or you can also just say that x equals 2, comma, negative 2/5, right? Each is a solution. Now, again, if you want to check this, you could plug a 2 in for x. And you could also plug a negative 2/5 in for x. And you would see that the left and the right side are equal. So let's go ahead and check it. So the absolute value of 5 times 2 and then minus 4 is equal to 6. So 5 times 2 is 10. 10 minus 4 is 6. The absolute value of 6 equals 6. So 6 equals 6. So yeah, that's true. You can check that one off. Then the other one is negative 2/5. So negative 2/5. So 5 times negative 2/5, the 5s would cancel. You'd have negative 2 minus 4, which is negative 6. So you basically have the absolute value of negative 6, which we know is 6. So 6 equals 6 here. So this one checks out as well. So again, x equals 2 or x equals negative 2/5. Let's look at one that's a little bit more complicated. It's just more complicated because you don't have the absolute value operation isolated on one side. So we have 5 multiplied by the absolute value of negative 7x plus 3 equals 58. So your goal, if you get something like this, is to isolate the absolute value operation. So how can we do that? It's very, very easy. You just think about what's being done to that absolute value operation. You have multiplication, right? You're multiplying by 5, and you have addition, 3 is being added to it. So let's go ahead and subtract 3 away from each side to start. We'll get rid of that. We'll have 5 times the absolute value of negative 7x plus 3, and this equals 58 minus 3 is just 55. Now I can just divide both sides by 5. So I divide both sides by 5, And this would cancel with this. And so I have the absolute value of negative 7x plus 3 is equal to 55 over 5 is 11. So now I have it in the format that I've been looking at. And again, once I have it like this, it's very, very easy. I take my expression, so negative 7x plus 3. I set it equal to 11. And then I say or. I take my expression, so negative 7x plus 3. I set it equal to negative 11. Okay? Just solve each one. Very, very simple. So I'm going to subtract 3 away from each side of the equation. I'm going to get negative 7x is equal to 11 minus 3 is 8. Then I'm going to divide both sides by negative 7. And I'm going to get that x is equal to negative 8/7. Over here, let me subtract 3 away from each side. That cancels. You'll have negative 7x is equal to negative 14. Divide each side by negative 7. And you get that x is equal to positive 2. So let me erase this. So again, x equals 2. So you can leave this as your solution. Again, you could write it in solution set notation. You could put the comma. There's a zillion different things you can do, whatever you're more comfortable with. So let's go ahead and check this real quick. And then all the rest of them, I'll leave that up to you to check them on your own. So I would have 5 multiplied by the absolute value of, I'd have negative 7 times negative 8/7. So we know that this would cancel with this. The negatives would cancel, so I'm basically just going to have an 8 there. So I'd have 8 plus 3, which is just 11. So then plus 3 equals 58. So the absolute value of 11 is 11. So you have 5 times 11 there. That's 55, and then 55 plus 3 is 58. So this one's good to go. Over here, you have the 2 that's going to be plugged in for x. So 5 times the absolute value of. Negative 7 times 2 is negative 14. Negative 14 plus 3 is negative 11. But again, because I'm taking the absolute value there, it just becomes positive 11. So 5 times 11, then plus 3 equals 58. We already know that's true. 5 times 11 is 55. 55 plus 3 is 58. So we're good to go in each case. Again, our solution is x equals negative 8/7 or x equals 2. All right, let's take a look at another one. So suppose we had 4 multiplied by the absolute value of negative 7 minus 10x. Then we had plus 5, and this was equal to 17. Again, my goal here is to isolate the absolute value operation on one side and then to have a number on the other. Okay, so what I want to do, I want to just subtract 5 away from each side of the equation to start. So we know this would cancel. So we'll say we have 4 times the absolute value of, we have negative 7 minus 10x, and then this is equal to 17 minus 5 is going to give me 12. Scroll down and get some room going. All right, so to isolate the absolute value operation, I have 4 that's multiplying it. So all I need to do is divide both sides of the equation by 4. So we know that, again, this would cancel. I'll have the absolute value of negative 7 minus 10x. This will be equal to 12 divided by 4 is 3. So now we have this in the format of our absolute value operation equals some number. So the absolute value operation here is equal to some number. So I can set up my compound equation with or. So I just take the expression inside. In this case, it's negative 7 minus 10x. I'm going to set it equal to 3. Then or, I'm going to take my expression inside, so negative 7 minus 10x. And I'm going to set it equal to the negative of 3, so negative 3. And then I'm just going to solve these two equations here, and I'll have my solution. So on the left, I'm just going to add 7 to each side of the equation. I'll have that negative 10x is equal to 3 plus 7 is just 10. And now we can divide both sides of the equation by negative 10. And of course, this guy's going to cancel. I'll have x is equal to 10 over negative 10 is just negative 1. So that's one solution. Let's get our other solution over here on the right. So again, I'm going to add 7 to each side of the equation. This is going to cancel. I'll have negative 10x is equal to negative 3 plus 7 is going to be 4. So now let me scroll down and get a little bit more room here. If I divide both sides of the equation by negative 10, then this guy right here is going to cancel with this guy, and I'll have x is equal to 4 over negative 10. We know that's negative. They're each divisible by 2. 4 divided by 2 is 2, and 10 divided by 2 is, of course, 5. So I get x equals negative 2/5. So I can write this as x equals negative 1, or, my keyword or, x equals negative 2/5. Again, you can do the solution set notation, or you can just list them with a comma, whatever you want to do. All right, so let's take a look at some special case scenarios that come up when we're solving absolute value equations. So the first one we're going to talk about is the situation where you have no solution. So something like the absolute value of x is equal to -5. This guy would not have a solution. So no solution. Why is that the case? Well, we should know that the absolute value of some real number x is greater than or equal to 0. Because if I plug in a 0 here, I'd get 0. If I plugged in a negative here, I'd get a positive. And if I plugged in a positive, I would get a positive, right? This stems from the definition of absolute value. When you take the absolute value of the number, you want the distance from 0 to the number on the number line. So if it's 0, it's just going to be 0. If it's some negative, again, you'd get a positive. If it was a positive, it would just be a positive. Okay, so you're never going to get a negative result. So this guy would always be no solution. When we go back to our generic formula here, I said earlier that the absolute value of some expression ax plus b, if this is equal to k has to be non-negative. So if you have isolated this guy right here, the absolute value operation on one side, and on the other side you have a negative value, you can stop and say there's no solution. What you don't want to do is say there's no solution before you've isolated the absolute value operation on one side. That can lead to problems, okay? So you need to make sure you isolate first. All right, let's take a look at an example. So we have 9 times the absolute value of 5x minus 1, then plus 10 is equal to -44. So the idea here is that we want to isolate the absolute value operation on one side of the equation, and then we want a number on the other. But if that number on the other side happens to be negative, we're not going to have a solution. So don't just look at the negative over here on the right-hand side and assume that this guy is going to be a no solution to start. You've got to isolate the absolute value operation before you can make that determination. So I'm going to start by just subtracting 10 away from each side of the equation. And we'll cancel this. We'll have 9 times the absolute value of 5x minus 1. And this is going to be equal to -44 minus 10 is -54. So at this point, you pretty much know it's going to be no solution. But let's continue. Let's go ahead and divide both sides by 9. And of course, this will cancel. We'll have the absolute value of 5x minus 1 is equal to -54 over positive 9 is -6. So we know at this point there's no solution, right? There's no solution. We have isolated the absolute value operation on one side, and we have a negative number on the other. So we can just say that there's no solution like this. This is what I always do. I just write no solution. A lot of textbooks, again, will use the symbol for the null or empty set, which looks like this. That's fine too if you want to write that. It's basically anything you want to do. So again, I just want to emphasize here why there's no solution. There's no value I can plug in for x there, multiply by 5, and then subtract away 1, and then take the absolute value of it and get -6. Doesn't matter what this value is. Once I take the absolute value, it's either going to be 0 or positive. Okay, so it can never, ever, ever be -6. So that's why there's no solution. Now, let me show you one thing real quick. Just want to make sure we're crystal clear on this before we move on. If, for example, I change this problem, and I'm not going to go all the way through, but if I change this problem to a negative out in front, you will have a solution. Okay, let's work through that real fast. I'm not going to go all the way through, but I'll just show you. If I subtract 10 away from each side here, that would cancel. I'll have -9 times the absolute value of 5x minus 1 is equal to -44 minus 10 is -54. Now if I divide both sides by -9, what's going to happen? Let's scroll down and get some room. Well, we see that this guy right here cancels with this guy. So I've isolated the absolute value of 5x minus 1. But now -54 over -9 is +6. So I would have a solution here. I would have to set 5x minus 1 equal to 6, and then 5x minus 1 equal to -6. So I would have that compound equation with OR, and I would get two solutions there. I'm not going to go through that process, but I'm just making sure that you understand that just because I start with a negative on the right-hand side doesn't mean that I have no solution. You've got to get to the point where you've isolated the absolute value operation on one side and a number on the other. If the number is 0, then you're just going to have one solution, which we'll talk about in a minute. If it's positive, you're going to have two solutions. And if it's negative, you're going to have no solution. All right, let's think about another scenario we're going to come across. So suppose the absolute value of x was equal to just 0. Well, in this case, you're not going to have to set up a compound equation with or. You're just going to have one equation. The absolute value of x equals 0 only if x is equal to 0. Okay, that's the only possible solution there because the only number that has an absolute value of 0 is just 0. 0 doesn't have an opposite. If this was the absolute value of x is equal to 2, again, x could be 2 or it could be negative 2 because each have an absolute value of 2. But when you get 0 there, you only have one unique number that has an absolute value of 0, and that's just 0. So let's look at this equation here. So we have 4 times the absolute value of 2x minus 14, then plus 5 is equal to 5. So again, our goal is always to isolate the absolute value operation. And when I subtract 5 away from each side, you're going to immediately see you have a problem. You get 4 times the absolute value of 2x minus 14, and this is equal to 0. So if I divide both sides by 4, we know 0 divided by 4 is just 0. So I'm going to end up with the absolute value of 2x minus 14 is equal to 0. So this is a special case scenario, okay? You do have a solution here, but you only have one, okay? You're not going to get two. So you need to pay close attention to what to do here. So all we need to do is say that 2x minus 14 is just equal to 0. We're just going to solve that equation. So I'm going to add 14 to each side. And of course, this is going to cancel. We'll have 2x is equal to 14. Then we're going to divide both sides by 2. And I'm going to get that x is just equal to 7. So just one solution here, x equals 7. So lastly, let's think about what happens when we have two absolute value operations set equal to each other. So something like the absolute value of ax plus b is equal to the absolute value of cx plus d. So the way we think about this is two numbers or expressions can only have the same absolute value if they're equal to each other or if they're opposites of each other. So we would say ax plus b is equal to cx plus d. So in the first scenario, just remove the absolute value bars and set the two expressions that were inside of the absolute value bars just equal to each other. Then or, next you're going to remove the absolute value bars and you're going to put parentheses around one of the expressions and basically negate it, right? So you're going to put a negative sign in front of it or make it into its opposite. You can even put this as a -1 out in front just to make it crystal clear what you're doing. And it would be just as valid if I said or, and I put a negative out in front of ax plus b and said this is equal to cx plus d. Just don't make them both negative. Only make one of them negative because you need them to be opposites. So let's look at our example. We have the absolute value of 4x minus 5 is equal to the absolute value of 9x plus 7. So again, I'm going to drop the absolute value bars. So I'm just going to say this is 4x minus 5 is equal to 9x plus 7. So I'm going to solve that. Then you have or. I'm going to drop the absolute value bars. So I'm going to have 4x minus 5 is equal to, you have 9x plus 7. So I'm going to choose one of these expressions. It doesn't matter which one you want. Wrap it in parentheses and put a negative out in front, okay? You could do this one, or again, doesn't matter. You can do this one. You will get the absolute same answer. Just for the sake of what we did earlier, I'm going to go ahead and just wrap this around here and just be done with it, okay? So for the first one, I'm just going to solve this. I'm going to write this down here. So we have 4x, again, 4x minus 5 is equal to 9x plus 7. Let me scroll down and I'll come back up. So to solve this is very, very easy. We just add 5 to each side of the equation. That cancels. 4x is equal to 9x plus 12. We subtract 9x away from each side of the equation. And this is going to cancel. So what I'm going to have is 4x minus 9x is negative 5x. And this is equal to 12. We can go ahead and just divide each side of the equation by negative 5. And we're going to find that x is equal to negative 12 fifths. So let's erase all of this. We're going to keep that x equals negative 12 fifths. So I don't need this equation anymore. I'm just going to put x equals negative 12 fifths. And then I'm going to have my or here. I'm going to do it vertically. And then I'll have x equals something here. And we'll get that from this. Okay. So here I'm going to distribute my negative to each term. Again, if you have trouble with that, put a -1 there and then distribute. Okay, that's the easiest way to remember. So 4x minus 5 is equal to -1 times 9x is negative 9x. And then -1 times 7 is minus 7. Now, what I want to do is add 5 to each side of the equation and add 9x to each side of the equation. So this is going to cancel. and this is going to cancel. 4x plus 9x is 13x. This is equal to negative 7 plus 5, which is negative 2. If we divide each side by 13, we're going to get that x is equal to negative 2/13. So x equals negative 2/13. In this lesson, we want to review solving absolute value inequalities. So in the last lesson, we talked about solving absolute value equations. In this lesson, we're just going to go one step further and talk about solving absolute value inequalities. Now, before we kind of jump into some problems, let's just take a moment here and think about absolute value as a concept. So if I asked you for the absolute value of something like the number 5, what am I asking you for? Remember, the absolute value of a number is the distance from 0 to that number on the number line. So if I want to know the absolute value of 5, I'm asking how far away is 5 from 0 on the number line? We know with any positive number, it's just the number, right? So 5 would be 5 units away from 0, and we can show that. It's 1, 2, 3, 4, 5, right? And it doesn't matter that I started at 0 and went to 5. I could start at 5 and go to 0. We're not measuring anything to do with direction. We're measuring the distance, okay? That's what we're focused on. So the absolute value of 5 would just be 5. The absolute value of, again, any positive number is just the number. So if I wanted the absolute value of, let's say, 8, it's just 8. If I wanted the absolute value of 1 million, it's just 1 million, right? So on and so forth. Now, when we work with absolute value, we've got to be aware of some of the restrictions or things that happen when we take the absolute value of a number. If I take the absolute value of a negative, I end up with a positive, right? So the absolute value of negative 5 would be what? Let's go to negative 5 on the number line, and I'm also 5 units away from 0. So I would go 1, 2, 3, 4, 5 units to get to 0. So this answer here is also 5, right? So I took the absolute value of something that's negative, and I got a positive. Because I'm measuring a distance with absolute value, I can never get a negative result, okay? You can think about distance as it relates to you driving in a car. Let's say you want to go to the grocery store. You can either get in your car and decide not to go, right? You just play some tunes in the car, and then you get lazy and decide, hey, I'm not going today. Or you can go some positive amount, right? But you can never go a negative distance. The only thing you can do besides getting a positive result is you can get 0 as a result, okay? If I took the absolute value of 0, I would get 0. And that's because 0 is 0 units away from itself on the number line. So the main thing to understand here is that the absolute value operation is always going to give you a result that is non-negative. So 0 or positive, okay? Very important you understand that because it will come up later on in the lesson. Now, we also want to think about one other thing here. I want you to notice that 5 and negative 5 have the same absolute value, right? If I did 8 and negative 8, those would also have the same absolute value. Okay, so numbers like these, 5 and negative 5, or 8 and negative 8, or 2 million and negative 2 million, these are known as opposites, okay? They're going to have the same absolute value, okay, because they're the same distance away from 0, but they lie on opposite sides of the number line. One's on the negative side, one's on the positive side, so we call them opposites. All right, so now that we understand the concept of absolute value, let's think a little bit about how we can solve an absolute value inequality. We're just going to start with some very simple examples here, and then we'll get into some more challenging material. So we're going to start with the absolute value of x is greater than 5. So using our understanding of absolute value, what am I asking for? What can I plug in for x here that would satisfy the inequality? Well, remember, if I'm taking the absolute value of something, I want to know the distance from that to 0 on the number line. The absolute value of x is greater than 5 is saying that x can be any value whose distance from 0 is greater than 5. So to find this, I could start at 0, and I could go 5 units to the right, and I could shade from 5 on, but 5 wouldn't be included because it's got to be strictly greater than 5. So I'll put a parenthesis at 5, or you can use an open circle if you want, if that's what you're doing in your class. And I want to shade everything to the right here because that would be part of my solution, right? So if I plugged in a 6 there, absolute value of 6 is 6. 6 would be greater than 5. That's true, okay? So that would work. If I plugged in an 8, the absolute value of 8 is 8. 8 is greater than 5. That's true. So any number larger than 5 would work. That's pretty obvious. Everybody gets that. But also, I've got to look in the other direction of 0 because, again, when we think about absolute value, it's a distance. So I can also travel to the left. I can go 1, 2, 3, 4, 5 units here. So anything less than -5 would work as well. -5 does not work. So I'm going to put a parenthesis there. And again, you can use an open circle if that's what you're doing. And then I would shade everything to the left here. And then we could try some numbers out in this range. Let's say we picked -7. So we plug in a -7 for x. The absolute value of -7 is 7. 7 is greater than 5. That's true. So what we have here for our solution is a compound inequality with or. Okay? So we can basically say that our solution is that x is greater than 5, or, remember our keyword or, x is less than -5. So we could also notate this in interval notation, right? It would be the union of the two solution sets. So I would have from -infinity out to, but not including, -5. And then the union with, you have anything larger than 5. So a parenthesis next to 5, again, out to positive infinity, okay? Notice how I used a parenthesis with each, with -5 and 5, because they're not included. All right, so let's look at a general rule that we can follow when we're solving these guys. And this first rule I'm going to give you is just the simplest case scenario. We'll look at a different rule in a minute that will cover more challenging problems. So we saw that the absolute value of x is greater than 5 led to x is greater than 5 or x is less than -5. So in general, the absolute value of x is greater than k. So this is a greater than case where we say that k is greater than 0. Okay, this has to be the case to use this rule. Then what's going to happen is we set up a compound inequality with or. So x can be greater than k, or you could say the negative of x, because the absolute value will make that positive, is greater than k. Now, what happens here, when you see this in your textbook, what they do is they divide both sides by -1 so that it's solved for x. And so you're going to get that x is less than. Remember, if you divide by a negative, you've got to flip the direction of the inequality symbol. So a greater than becomes a less than. And then k over -1 is just -k. So what we see is that x can be greater than k, or x can be less than -k. Okay, so this is what you're going to see. And again, when we worked with this first example here, where we said that the absolute value of x is greater than 5, we got just this. X was greater than 5, or x was less than -5. Okay, so that's where that comes from. So if I gave you a problem, like let's say the absolute value of x is greater than 14, well then you can very quickly say that x is greater than 14, or x is less than -14. Okay, the first scenario, you just remove the absolute value bars. So in this case, it would just be x is greater than 14. The second scenario, you just think about it like this. Flip the direction of the inequality symbol, so my greater than becomes less than, and then change the sign of the number out here. So from 14, I get -14. So if you could just remember that, you flip the sign and then make the number negative, you're good to go. Okay, that's all you need to remember. So let's look at our rule when it's more complicated. So when we get more challenging problems, we're not going to always have the absolute value operation isolated to start. So we've got to get it in this format of the absolute value operation on one side and a number on the other, okay? Notice how I've said that k is greater than 0. Again, if it's 0 or less than that, we'll talk about those special cases at the end of the lesson. But I want to isolate this to where the absolute value of some expression ax plus b is greater than k. So this is going to set up to this expression ax plus b is greater than k, or ax plus b is less than the negative of k. All right, so same process. For the first one, I just remove the absolute value bars. I copy what's there. It's very simple. For the second one, I remove the absolute value bars so the expression doesn't change. I flip the direction of the inequality symbol, so now it's a less than, and then I make that number negative. So instead of just k, it becomes -k. All right, so let's look at an example. All right, so for this one, we have the absolute value of 2x plus 3 is greater than 17. So the first case is I just remove the absolute value bars. So I'll have 2x plus 3 is greater than 17. Then or, my second case, I remove the absolute value bars. So 2x plus 3. I flip the direction of the inequality symbol, so it's a less than. And then I make this number negative. So it's going to be a -17. Okay? And if you have trouble remembering that, you can always just make the expression over here. you could always say it's the negative of this guy. So the negative of 2x plus 3 is greater than 17. When you divide both sides by -1, you're going to get it into that format. So this would flip, and this becomes negative. Okay, so that's another way you can kind of remember it. All right, so let's quickly solve these two inequalities. For this one, I would just subtract 3 away from each side. I would get 2x is greater than 17 minus 3 is 14. Divide both sides of the inequality by 2. I get x is greater than 7. Okay, over here, if I subtract 3 away from each side of the inequality, that cancels. I get 2x is less than negative 17 minus 3 is negative 20. Divide both sides by 2, and we're going to get that x is less than negative 10. Okay, so we got that x is greater than 7 or x is less than negative 10. So let's erase this. Okay, so let me put my or here. So you could write it like this as your solution. You can, of course, do interval notation. So from negative infinity up to but not including negative 10. So it's the union with, you've got not including 7, and then up to positive infinity. Okay, so negative 10 is not included, you've got a parenthesis there. 7 is not included, you've got a parenthesis there. Now graphically, on our number line, we can put a parenthesis at 7, and we can shade everything to the right. Okay, all that. And then in terms of x being less than negative 10, we don't have a notch for negative 10, but we can just make one real quick. So we'll say this is negative 10, and let me make that a little bit better. And then I'm just going to put a parenthesis there, and I'm going to shade everything to the left. All right, let's take a look at another one. So suppose we have 10 times the absolute value of negative 4x minus 5 plus 2 is greater than 72. So again, the idea here is to isolate the absolute value operation on one side, have a number on the other. So what I'm going to do is I'm just going to subtract 2 away from each side of the inequality to start. That cancels. You've got 10 times the absolute value of negative 4x minus 5. And this is going to be greater than 72 minus 2 is 70. So now, since 10 is multiplying this absolute value operation, I can just divide both sides of the inequality by 10. So that cancels. Now I've isolated the absolute value operation. I've got the absolute value of negative 4x minus 5 is going to be greater than 70 over 10 is 7. Okay, so let me erase this. All right, so we know our scenario here with a greater than. We want to remove the absolute value bars. So negative 4x minus 5 is greater than 7. Then or, we want to remove the absolute value bars. So negative 4x minus 5. We want to flip the direction of the inequality symbol. So this is less than. We want to make this negative. So this is negative 7. Okay, so let's solve our compound inequality. Let's add 5 to each side of the inequality. That cancels. You get that negative 4x is greater than 12. We divide both sides by negative 4. Remember, this has the flip. We divided by a negative, so this is a less than now. So you've got x is less than. 12 over negative 4 is negative 3. Over here, if I add 5 to each side of the inequality, that cancels. You're going to get negative 4x is less than. Negative 7 plus 5 is going to be negative 2. We divide both sides by negative 4. Again, if I divide by a negative, I've got to flip that guy. So this becomes a greater than. So we have x is greater than. Negative 2 over negative 4 is positive 1/2. All right, let's erase everything. So we can write our solution as x is less than negative 3 or x is greater than 1/2. Again, in interval notation, you're coming from negative infinity up to but not including negative 3. So the union with, you don't include 1/2, but out to positive infinity, okay? So again, negative 3 and 1/2 are not included. You have a parenthesis next to each. So now graphically at negative 3, I'd put a parenthesis facing to the left, and I would just want to shade everything going to the left here. So all of that. And then at 1/2, which would be about right here, let's say, I'm going to say that's 1/2. I'm going to go ahead and put a parenthesis there. So let's put a parenthesis there. And again, let's just shade everything to the right. Okay, so that's my solution region. All right, now let's talk about the other scenario, which is when we have a less than. So if I had the absolute value of x is less than 5, I'm going to follow the same procedure, but I'm going to use an and compound inequality. So in other words, I'm going to remove the absolute value bars. So I'm going to say x is less than 5. Then I'm going to say and. Then the next one, I'm going to remove the absolute value bars. So I'm going to have x. I'm going to flip the direction of the inequality symbol, so this is greater than. I'm going to make the number negative, so this is a negative 5. So it's the exact same process, but we're using an and now, okay, because we're going to have a between. So x will be between negative 5 and 5. You could really write this as a three-part inequality and say that negative 5 is less than x, which is less than 5, or you could read that as x is greater than negative 5 and less than 5. Now, conceptually, why does this make sense? I'm asking for all the numbers whose absolute value or whose distance from 0 is less than 5. Again, if I started at 0 and I went 5 units to the right, I couldn't be 5 because it's got to be less than 5. So I'd put a parenthesis there facing to the left. If I started at 0 and went the other way, again, I'd go 5 units. It couldn't be negative 5, but it could be anything greater there. So it would have to be between negative 5 and 5 on the number line. Those are the only values that would satisfy this. If I plugged in a negative 2, the absolute value of negative 2 is 2. 2 is less than 5. That works. If I took something outside of the range, let's say I took 6. The absolute value of 6 is 6. 6 is not less than 5. So it's got to be in that range of numbers to work and satisfy that inequality. If we see something more complex, we can just write down this rule. So I isolate my absolute value operation on one side. It's the same thing we saw with the greater than, but just now I'm going to have an and. So it's the exact same procedure. So the absolute value of ax plus b is less than k, where k is greater than 0. We say we have ax plus b is greater than negative k, and ax plus b is less than positive k. So again, the first scenario, just remove the absolute value bars. So that's this here. The second scenario, remove the absolute value bars, flip the direction of the inequality symbol, so you get a greater than, and then make this number out here negative, okay? The only difference is you're using an and statement. So really, if you want to make this easier on yourself, just write it as a three-part inequality. So the expression goes in the middle, and it's greater than the negative of this, and it's less than the positive of this. All right, let's take a look at an example. So suppose we have the absolute value of 8x plus 4, and this is less than or equal to 52. Well, this guy's already isolated for me, so I don't have a whole lot of work here. All I've got to do is follow my rule. So I'm going to drop my absolute value bars. I'll have 8x plus 4 is less than or equal to 52. Then and, okay, I'm going to drop my absolute value bars. So 8x plus 4, flip the sign, so this becomes a greater than or equal to, make 52 negative. So it's negative 52. Now, I would advise when you solve these to put it as a three-part inequality because it's just easier to work with. So I'm going to put that negative 52 is less than or equal to 8x plus 4, which is less than or equal to the number 52. So if I want to solve for x in the middle, I would subtract 4 away from each part. Let me scroll down and get some room going. So on the right-hand side, 52 minus 4 is 48. And then this cancels, so I've just got 8x in the middle. On the left-hand side, negative 52 minus 4 is negative 56. All right, so to get x isolated in the middle, I'm going to divide each part by 8. Let me make that a little better. So negative 56 divided by 8 is negative 7. This is less than or equal to, 8 over 8 is 1, so we just have x here in the middle. This is less than or equal to, 48 over 8 is 6. So I have that x is basically between negative 7 and 6, and negative 7 and 6 are both included here because we have non-strict inequalities. So let me erase all this. And again, we can write this in interval notation. We can use a bracket here at negative 7, and then a bracket at 6 to show these are both included. On the number line, I can use a similar process. So at negative 7, I put a bracket. At 6, I'm going to put a bracket. And let me make that a little better. And again, I'm just going to shade everything between here. So from negative 7 to 6, all those numbers work, including negative 7 and 6. All right, let's look at another one. So we have 6 times the absolute value of negative 3x plus 9, then plus 4 is less than or equal to 94. So again, I've got to isolate my absolute value operation so I can use my little rule. So I'm going to subtract 4 away from each side of the inequality. That cancels. I've got 6 times the absolute value of negative 3x plus 9. This is less than or equal to 94 minus 4 is 90. So now I'm going to divide both sides by 6 because that's what's multiplying this absolute value operation. So let me get some room here. This cancels. We'll have the absolute value of negative 3x plus 9 is less than or equal to 90 over 6 is 15. Okay, let me get a little bit more room. So now we're ready to set up our compound inequality with and. So again, first scenario, just remove the absolute value bars. So negative 3x plus 9 is less than or equal to 15. Then and, okay, you've got negative 3x plus 9. Again, remove the absolute value bars. Flip the sign, so it's a greater than or equal to. Make this negative. So this is negative 15. And again, it's easier to just write this as a three-part inequality. Just makes it faster to solve. So negative 15 is less than or equal to negative 3x plus 9, which is less than or equal to 15. All right, let's solve this guy. So we're going to subtract 9 away from each part here. Negative 15 minus 9 is going to be negative 24. This is less than or equal to. You've got your negative 3x here, and this cancels. And this is less than or equal to. 15 minus 9 is 6. All right, so to get x by itself, let's divide each part by negative 3. And remember, even though it's a three-part inequality, we've still got to flip these signs. Very important you do that, okay? Otherwise, you will get the wrong answer. So x is going to be in the middle by itself. I'm going to flip the signs to greater than or equal to. Negative 24 over negative 3 is positive 8, and 6 over negative 3 is negative 2. So I'm just going to reorder this and say this is x is greater than or equal to negative 2, and it's less than or equal to 8. So let's erase everything. All right, so let's go ahead and write this in interval notation. Again, our endpoints are included here, so I'll put a bracket and then a negative 2, and then I'll put 8 and then a bracket. Okay, so this is interval notation. Again, negative 2 and 8 are both included, so we use our brackets. Then on my number line, I could put a bracket at negative 2 and a bracket at 8. I could just shade everything in between. So that's my solution region. Again, from negative 2 to 8 with negative 2 and 8 included. All right, now let's talk about the special case scenarios that come up. Basically, you have to think about things. If you get a right side of 0 or a negative, you have to think about what's going on, okay? If I get something like the absolute value of x is greater than or equal to 0, this is true for all real numbers, okay? So if you get the absolute value isolated on one side and it's greater than or equal to the number 0, it's true for every real number because the absolute value operation is either 0 or some positive amount. So if the result from your operation is 0, you're okay, right? It works. If it's some negative, it still works, right? Because you're going to get a positive. If it's positive, it still works. So every real number would be greater than or equal to 0 when it's run through the absolute value operation. So this is all real numbers, okay, for an answer. For the absolute value of x is greater than or equal to negative 5, again, absolute value is always non-negative. So it's always going to be 0 or higher, and it's always going to be greater than the number negative 5, right? It'll never be equal to it, but if it's a negative value, it'll always be greater than that. So this is also true for all real numbers. Okay, so if you see a negative over here and you've got a greater than, all real numbers is your solution. All right, what if you've got a less than and a negative over here? Well, here you can't get a solution, right? The absolute value of x is less than negative 5. That's not possible, okay? It can never be less than a negative. It can't be less than 0, okay? It can be 0 or positive. That's it. So for this guy, there's no solution, okay? Now, this one's a tricky one, okay? What if you saw the absolute value of x is less than or equal to 0? Well, we know that it can't be less than 0, but it can be equal to 0. So this one will have one solution. You basically need to set x equal to 0, and that's your solution. If x equals 0 here, that works, right? The absolute value of 0 is less than or equal to 0, right? 0 is less than or equal to 0. That is true, okay? But if I use any other number, it does not work, okay? So what I want to do with this type of scenario, if I've isolated the absolute value operation and it's less than or equal to 0, I just set that expression inside the absolute value bars equal to 0, and I solve, and that's going to be my solution. All right, let's look at a few examples. So we have negative 7 times the absolute value of 10x plus 4 plus 1 is less than or equal to 43. So again, we want to start by isolating the absolute value operation. So I'm going to subtract 1 away from each side of the inequality. That's going to cancel. I've got negative 7 times the absolute value of 10x plus 4, again, is less than or equal to 43 minus 1 is 42. All right, let's get some room going. So now I'm going to divide both sides of the inequality by negative 7. This cancels. I'm going to have the absolute value of 10x plus 4. Now I divided by a negative, so this has got to get flipped. So it's going to become a greater than or equal to 42 over negative 7 is negative 6. Now, you can stop here. The absolute value operation is isolated, and it's greater than a negative value. What did we say about that? The absolute value operation is always going to be 0 or some positive amount. So it will always be greater than negative 6. So this is true for all real numbers. So you can stop and say all real numbers. In interval notation, you can put from negative infinity to positive infinity. And if you wanted to show this on a number line, you could basically just shade the entire number line. Okay? This would be your graphical solution. Just shade the entire thing. All right, let's take a look at another one. So suppose we had negative 4 times the absolute value of 6x minus 8, then minus 6 is greater than 98. So again, I want to isolate this part right here first. Very important you do that. So let's add 6 to both sides of the inequality. That cancels. You've got negative 4 times the absolute value of 6x minus 8. And this is greater than 98 plus 6 is 104. Let's divide both sides by negative 4. So we know this cancels. I've got the absolute value of 6x minus 8. This is going to get flipped, so it'll become a less than. Then 104 over negative 4 is negative 26. Now, can the absolute value of something ever be less than negative 26? No, it cannot. Again, it's got to be 0 or some positive amount. So it doesn't matter what I plug in here for x. Whatever this result here is inside the absolute value bars, once I take the absolute value, it's going to be 0 or positive. So it can never, ever, ever be less than negative 26. So there's no solution here. No solution. Okay? And again, you can put that symbol for the null or empty set. All right, let's take a look at one more. So we have 4 times the absolute value of 8x minus 2 is less than or equal to 0. So again, I can divide both sides by 4 so that I can isolate the absolute value operation. So this cancels. I get that the absolute value of 8x minus 2 is less than or equal to 0 over 4 is 0. Now, the only way, again, that this works is if we set this expression here, 8x minus 2 equal to 0. Because it can never be less than 0. That's not ever going to work, right? Because once we take the absolute value, it's going to be 0 or something positive. So we can get it to equal 0, but we can never get it to be less than 0. So there's only one solution here. So 8x minus 2 is equal to 0. Add 2 to each side of the equation. You'll have 8x is equal to 2. We're going to divide both sides by 8. And we're going to get that x is equal to 2 over 8 is 1 over 4, okay, or 1/4. So the only way to make this true is if x is 1/4. This is not a range of values. If we looked at this on the number line, you would basically just go to 1/4. Let's say this is 1/4 here, and you would basically just put a dot there and say my solution is just that number.